Imagine standing at a crossroads where you must choose left or right, and in that moment before you decide, the universe itself seems to hold its breath, waiting for your decision to collapse all possibility into a single reality. According to the many worlds interpretation, this breath is never actually released, because both paths are taken simultaneously, each one spawning an entirely separate branch of reality where you experience a different outcome. This interpretation of quantum mechanics, first proposed by physicist Hugh Everett in 1957, suggests that whenever a quantum event occurs with multiple possible outcomes, the universe does not randomly select one result while discarding all others, but rather creates a new parallel universe for each possibility. And in each of these branches, you exist in a slightly different form, making different choices, living different lives, experiencing different consequences. The mechanism underlying this concept emerges from a fundamental problem in quantum physics, the measurement problem, which describes how the act of observing a quantum system forces it to choose a definite state, when before observation it existed in what physicists call a superposition, a strange state of being multiple things at once. Rather than accepting that observation somehow causes reality to collapse into one possibility, the many worlds interpretation proposes that observation does not eliminate alternate possibilities, but rather causes the observer to branch into multiple versions of themselves, each experiencing one of the possible outcomes as their singular reality. What makes this interpretation psychologically compelling, despite its profound counterintuitiveness, is that it removes the mysterious element of randomness from quantum mechanics by suggesting that all possibilities are equally real, equally actualized, simply existing in separate branches of reality that never interact or commune. Imagine standing at a crossroads where every decision you make spawns a new reality in which you made the opposite choice, and this happens not just for you, but for every particle, every atom, every quantum event across all of existence simultaneously, creating an incomprehensibly vast landscape of branching universes that extend infinitely in directions we cannot perceive or measure. The infinite parallel universes theory suggests that our universe is merely one thread in an infinite tapestry of worlds, each with its own unique set of circumstances, physical laws, and outcomes, where somewhere there exists a version of you who chose differently at every critical juncture of your life. This concept emerges from several legitimate scientific frameworks, particularly from quantum mechanics and the many worlds interpretation, which proposes that every quantum event that could happen does happen, but in separate, equally real universes that split off from one another instantaneously and irreversibly. The psychological appeal of this theory lies in its profound comfort, as it suggests that all possibilities are actualized somewhere, that no choice is truly final, and that every version of yourself that could exist does exist, relieving us of the crushing weight of determinism and chance that defines a singular timeline. We accept this theory despite its radical unfalsifiability, because it provides a philosophical escape from the anxiety of finitude and irreversibility, transforming the terror of a single path through time into the liberating notion of infinite paths, all occurring simultaneously in parallel dimensions beyond our reach. The theory has persisted in popular culture and scientific discourse because it elegantly reconciles quantum mechanics with our intuitive sense that possibility precedes actuality, and because contemplating it induces a meditative state where responsibility dissolves and all outcomes become equally valid in T. Imagine a universe that never truly stops inflating, where the expansion that we believe happened in the first fraction of a second after the Big Bang continues eternally across vast regions of space, each one expanding at such tremendous speeds that they become causally disconnected from one another, unable to exchange information or influence, creating pocket universes that bud off like bubbles in an infinite cosmic foam. Each with its own physical laws and constants, while the underlying quantum field that drives inflation continues its relentless work in the spaces between them. This is the essence of eternal inflation, a theoretical framework that emerged from the work of physicists like André Linde in the 1980s, proposing that the inflationary epoch which shaped our observable universe is not a singular event with a definite beginning and end, but rather an ongoing process that generates new universes perpetually across an infinite multiverse. The mechanism rests upon a curious property of quantum fields in the early universe, where the energy density of the inflatoned field fluctuates at tiny scales, and in some regions these fluctuations can cause expansion to slow and end, creating bubble universes like our own with specific physical parameters, while in other regions the field maintains its high-energy state and continues inflating, spawning more bubbles in a never-ending process of cosmic reproduction. What persists in this theory, despite its mind-bending implications, is how naturally it flows from our best mathematical descriptions of inflation itself, how elegant the equations appear, and how it has become woven into the fabric of serious cosmological discussion without requiring extraordinary new physics, merely extending the logical consequences of inflation to their ultimate conclusion, suggesting that our entire universe might simply be one infinitesimal bubble among an eternally inflating multiverse where countless O. Imagine standing in a vast desert where every grain of sand represents an entire universe with its own set of physical laws, and you begin to approach the concept known as the string theory landscape. Within the mathematical framework of string theory, physicists discovered that the equations describing how tiny vibrating strings compose all matter and energy do not yield a single unique solution, but rather an almost incomprehensibly large number of possible solutions, estimated somewhere between 10 to the power of 100 and 10 to the power of 500. Each of these mathematical solutions corresponds to a different possible universe with different fundamental constants, different forces, different particle types, and different ways that the dimensions of space and time could be organized and curled up at scales too small for us to observe. The mechanism underlying this proliferation of possibilities emerges from the geometry of extra dimensions that string theory requires, dimensions beyond the four we perceive, and the various ways these hidden dimensions can be compactified or folded into themselves creates an enormous combinatorial space of potential configurations. This landscape suggests that rather than one universe governed by one immutable set of laws, reality might consist of an unimaginably vast collection of pocket universes, each instantiating different physical laws and constants, with our own universe representing merely one point in this infinite dimensional space of possibilities. The profound oddness of this conclusion persists within modern theoretical physics despite lacking direct observational evidence, largely because string theory remains the most mathematically elegant and comprehensive framework yet developed for potentially unifying quantum mechanics with general relativity, and the landscape emerges necessarily from its equations rather than as an optional feature. Imagine the fabric of existence not as a single unified cosmos, but rather as an infinite expanse of foam, where countless universes exist as distinct bubbles, each one complete with its own physical laws, constants, and dimensional structure, separated from one another by the vast stretches of expanding spacetime that constitute the boundaries between them. This concept, known as bubble universe theory or cosmic inflation, emerged from the work of physicists including André Linde and has become increasingly central to modern cosmological thinking, suggesting that what we perceive as the entire universe is merely one bubble among an incomprehensibly vast collection of such universes, each potentially harboring entirely different conditions for matter, energy, and consciousness to emerge. The mechanism behind this theory rests on the understanding that during the earliest moments following the Big Bang, the universe underwent a period of exponential expansion called inflation. And according to the mathematics of quantum field theory, this inflationary process does not necessarily occur uniformly across all of spacetime, but rather can produce regions where inflation ends while other regions continue expanding eternally, creating bubble-like pockets of universe separated by inflating space. What makes bubble universes particularly compelling to contemplate is how this concept has gradually shifted from speculative fringe theory to a respected framework within mainstream cosmological discourse, accepted by numerous physicists, and incorporated into serious models attempting to explain our universe's seemingly improbable constants and initial conditions. Despite the fact that we possess no direct observational evidence that these bubbles exist and may never develop the technological capacity to detect them, yet we have somehow normalized this profound notion of infinite unseen universes as a reasonable scientific proposition rather than treating eye. Imagine yourself standing at the edge of a profound thought experiment that challenges everything we understand about consciousness, probability, and the nature of existence itself. Quantum immortality emerges from a peculiar intersection of quantum mechanics and subjective experience, suggesting that from your own perspective, you might never actually experience death, no matter how statistically improbable your survival becomes. The mechanism works like this. According to quantum mechanics, particles exist in superposition until observed, existing in multiple states simultaneously until measurement collapses those possibilities into a single reality. When applied to a thought experiment involving a quantum suicide scenario, the logic suggests that while external observers might see you die, your consciousness would always find itself in the branch of reality where you survived, however improbable that branch becomes. This creates a deeply unsettling implication where you would experience an increasingly miraculous string of survivals, where bullets miss by infinitesimal margins, where terminal diagnoses suddenly reverse, where accidents that should have killed you instead leave you unscathed. Your subjective experience would be one of impossible luck cascading upon itself endlessly, a personal timeline growing ever more improbable as you age beyond reasonable lifespans. The theory persists despite having no empirical evidence and despite contradicting our intuitive understanding of how consciousness relates to the physical world, yet it haunts the edges of serious discussions about quantum mechanics and the many worlds interpretation. We have grown comfortable with this idea existing in scientific thought precisely because it cannot be disproven from within any single subjective experience, creating a philosophical loop that seems to demand acceptance simply through the act of contemplating it. Imagine standing before a perfect reflection, and then consider the possibility that this reflection is not merely light bouncing back at you, but rather a genuine parallel world existing in perfect symmetry to our own, where every atom, every star, every conscious thought has an exact opposite counterpart arranged in reverse. Mirror universe theory proposes that for every universe with its particular laws of physics and arrangement of matter, there exists an identical universe where everything is flipped along some fundamental axis, creating a kind of cosmic duality that extends beyond what our eyes can perceive. This concept emerges from the mathematical properties of symmetry that physicists have observed throughout nature, where countless physical processes appear to work equally well whether played forward or backward, suggesting that the universe itself might possess this reflective quality at the deepest level. The psychological appeal of mirror universes lies in our intuitive understanding of symmetry as a fundamental principle of beauty and balance, combined with our observation that nature frequently employs symmetry in its most elegant solutions, from the spiral of galaxies to the double helix of DNA to the mirror image of our own left and right hemispheres. We find comfort in the notion that reality possesses this kind of perfect balance, that for every choice we make, there exists another version of ourselves making the opposite choice in a reflected realm, creating a sense of cosmic equilibrium and completeness. Yet despite the mathematical elegance supporting certain symmetries in physics, the idea of entire mirror universes remains largely speculative and untestable by current scientific methods, existing more as a thought experiment that helps us explore the boundaries of theoretical physics rather than as an established framework supported by observable evidence. Imagine for a moment that everything you perceive, every sensation and thought and memory, exists within an elaborate computational system designed by an intelligence far beyond our comprehension, and that the laws of physics themselves are simply lines of code running on some incomprehensibly vast computer. This is the essence of simulation theory, a hypothesis that has moved from the margins of philosophical speculation into serious consideration by physicists, technologists, and philosophers who examine the nature of reality itself. The idea suggests that our universe, with its fundamental constants, its quantum mechanics, and its seemingly fine-tuned parameters that allow for the existence of conscious beings, might be artificially created rather than naturally occurring, designed to run like software on hardware constructed by some parent civilization or superintelligence. What makes this theory psychologically compelling is that it operates on a kind of recursive logic that becomes increasingly difficult to dismiss as we advance our own computational capabilities. We observe that our technology trends toward greater simulation capacity, that we create more sophisticated virtual worlds and artificial intelligence systems with each passing year, and it becomes reasonable to extrapolate that future civilizations would achieve the ability to create complete simulated universes complete with conscious observers. Once that technological possibility exists, the probabilistic mathematics becomes unsettling, because if it is possible to create such simulations, then likely many would be created, meaning the ratio of simulated universes to base-level universes would be enormously skewed toward simulation. Therefore, statistically speaking, you are far more likely to be living in a simulation than in the original base reality. Imagine standing in a vast library where every possible book that could ever be written already exists on the shelves, not as physical objects but as pure mathematical structures. And according to the mathematical universe hypothesis proposed by physicist Max Tegmark, this library is not a metaphor, but rather the fundamental nature of reality itself. The hypothesis suggests that the universe is not made of matter or energy or even quantum fields, but instead exists as a mathematical structure, meaning that physical reality is nothing more than abstract mathematics made tangible through our perception of it. This concept emerged from observations that the universe appears to follow mathematical laws with extraordinary precision, from the orbits of planets to the behavior of subatomic particles, leading some physicists to wonder whether mathematics is simply a useful tool we invented to describe reality, or whether mathematics is the actual underlying substance of reality. The hypothesis proposes that not only is our universe mathematical in nature, but that all possible mathematical structures that can exist must exist as actual universes somewhere within a grand multiverse, suggesting that there is no special selection process determining which mathematical structures become real and which remain abstract, but rather that every conceivable mathematical universe is equally real and equally valid. The psychological appeal of this idea lies in its radical simplicity and its resolution of certain philosophical puzzles about why mathematics is so unreasonably effective at describing the physical world. Yet the hypothesis persists despite its profound strangeness, and despite the fact that it makes the existence of infinitely many universes a mathematical necessity rather than a speculative possibility, leaving us to contemplate whether consciousness itself might be a mathematical phenomenon and whether our sense of existing in a unique. As we venture deeper into theoretical physics and the nature of reality itself, we encounter what physicist Max Tegmark termed the level IV multiverse, a concept so abstract and philosophically ambitious that it challenges not merely our understanding of space and time, but the very foundations of mathematical existence and physical law. The level IV multiverse proposes that all mathematically consistent universes must exist somewhere in a grand cosmic landscape, that every possible mathematical structure that could coherently describe a universe does in fact exist as a real, tangible realm somewhere beyond our observable horizon. This framework suggests that what we call the laws of physics are not fundamental truths handed down by some cosmic principle, but rather emergent properties of the particular mathematical universe we inhabit, one among infinitely many equally valid mathematical realities where different constants, different dimensions, and entirely different logical structures govern existence. The mechanism behind this proposition rests upon a profound philosophical shift in how we understand mathematics itself, moving from seeing mathematics as merely a language humans invented to describe nature, to viewing mathematics as the fundamental substrate of reality itself, suggesting that existence and mathematical consistency are one and the same thing. Our minds seem to struggle not because this idea is logically flawed, but because it strips away our intuitive sense that reality requires some external justification or designer, forcing us instead to confront the possibility that reality simply exists because mathematical existence is self-justifying, and any universe that can mathematically exist simply must exist somewhere in this infinite collection. Imagine our universe not as the totality of existence, but merely as a thin, three-dimensional membrane floating in a higher dimensional space, much like a sheet of paper suspended within an infinite room. This is the essence of Brane cosmology, a theoretical framework emerging from string theory that proposes our familiar four dimensions of spacetime are actually contained within what physicists call a brane, while gravity and other fundamental forces might extend into additional spatial dimensions beyond our perception. The theory suggests that parallel universes could exist as separate branes stacked alongside ours, separated by distances so infinitesimally small that they might occupy the same physical space, yet remain completely invisible and inaccessible to us, which naturally leads to the contemplation that countless other worlds might brush against the very fabric of our reality at this very moment without our knowledge. What makes Brane cosmology particularly fascinating from a conceptual standpoint is how it resolves certain perplexing problems in physics, such as why gravity appears so much weaker than other fundamental forces, proposing that gravitational effects leak away into these hidden dimensions, while electromagnetism and nuclear forces remain confined to our brain. The psychological appeal of this framework lies in its elegant transformation of the invisible into the rational, converting our intuitive sense that something exists just beyond our comprehension into a mathematically rigorous possibility grounded in string theory and the mathematics of higher dimensions. We find ourselves drawn to this idea because it validates a deep human suspicion that the universe contains hidden layers of complexity, yet simultaneously provides us the comfort of knowing that these mysteries operate according to elegant mathematical principles rather than arbitrary chaos. Imagine standing in a completely dark room and being told that just beyond the walls surrounding you exists an entire universe that you cannot perceive, not because it is far away, but because it exists in a direction your eyes and mind are fundamentally incapable of comprehending. This is the concept at the heart of higher dimensional universes, a theoretical framework suggesting that our familiar three spatial dimensions plus time might represent only a fraction of the actual dimensional structure of reality. Physicists and mathematicians have proposed that additional dimensions could exist perpendicular to our own, curled up so tightly at scales smaller than we can measure that they remain invisible to our current instruments and senses. String theory, one of the most ambitious attempts to unify quantum mechanics with gravity, actually requires anywhere from 10 to 11 dimensions to function mathematically, treating these extra dimensions not as mathematical conveniences, but as genuine features of the cosmos. The mechanism underlying this concept draws from pure geometry and mathematical necessity rather than direct observation. When physicists write equations describing fundamental forces and particles, they find that the mathematics only resolves into consistent, non-contradictory solutions when extra dimensions are included in the framework, as though the universe itself is whispering through equations that it contains more than we can see. The human mind, evolved to navigate three spatial dimensions, struggles to visualize what a four-dimensional object would actually look like, let alone higher dimensions, yet mathematically we can describe their properties with precision and detail. Despite the profound challenge of proving these dimensions actually exist and the absence of direct experimental evidence, the framework persists in theoretical physics because it solves problems that other approaches cannot address, suggesti. Imagine for a moment that every black hole in our universe contains within it an entirely separate universe, complete with its own stars, galaxies, and perhaps even life itself, and that our own universe might exist inside a black hole within some larger parent universe, creating an infinite recursive stack of realities nested within one another like cosmic Russian dolls. This is the concept of black hole universes, a theoretical framework that emerges from the intersection of general relativity and quantum mechanics, suggesting that the singularities at the hearts of black holes may serve as birthplaces for entirely new universes rather than representing true points of infinite density and destruction. The mechanism underlying this theory involves the observation that information entering a black hole's event horizon becomes causally disconnected from the external universe, and some theoretical physicists have proposed that what we experience as a black hole's singularity from the outside might actually be perceived as the Big Bang of a new universe from the inside, with the infalling matter and energy serving as the seed material for an entirely new cosmos with its own physical laws and constants. This idea persists in theoretical discourse despite remaining entirely untestable, because it elegantly resolves certain paradoxes in black hole thermodynamics and information theory, while simultaneously providing a framework for understanding the nature of infinity and recursion within the universe itself. And we have gradually normalized this once absurd concept by incorporating it into legitimate scientific conversations about quantum gravity and multiverse cosmology, allowing it to occupy a legitimate place in the landscape of serious theoretical physics, even as we acknowledge that direct observation or verification may remain forever impossible. Imagine standing at a crossroads where every decision you could possibly make has already happened somewhere, in some version of reality that exists just as completely as the one you inhabit right now. This is the essence of the many worlds interpretation of quantum mechanics, a framework suggesting that whenever a quantum event occurs with multiple possible outcomes, the universe doesn't choose one outcome and discard the others. Instead, it branches into separate, equally real universes where each possible outcome has occurred. When an electron can spin up or down, both versions happen simultaneously in different branches of reality. When you flip a coin and it could land heads or tails, both outcomes materialize in distinct, parallel versions of existence. The psychological mechanism that makes this theory so compelling is that it eliminates the arbitrariness of quantum collapse. Rather than accepting that nature randomly chooses outcomes through some mysterious process, the many worlds interpretation suggests that all possibilities are equally real and coexisting. This appeals to our sense of logical completeness because it avoids the troubling notion that reality requires an observer to collapse probability waves into actual events. Yet what's remarkable is how thoroughly this theory challenges our basic intuitions about singular existence while simultaneously offering a strange kind of comfort. We have normalized the idea that infinite versions of ourselves are constantly being created, each experiencing a different branch of reality, each making different choices that lead to different consequences, and somehow we find this oddly soothing rather than deeply unsettling. The theory persists not because we have direct evidence that these parallel branches exist, but because the mathematics works perfectly and the alternative explanations feel more philosophically troubling than accepting a multiverse of infinite possibility. Imagine standing before an impossibly complex control panel with countless dials, each one calibrated to an exact specification, and you begin to realize that if even a single dial were adjusted by the smallest fraction of a percent, the entire universe as we know it would collapse into either infinite density or infinite emptiness, leaving no possibility for stars, planets, or life itself to ever emerge from the cosmic void. This is the essence of the fine-tuning problem that has captivated physicists and philosophers for decades, a profound observation that the fundamental constants of our universe, the strength of gravity, the charge of the electron, the mass of the proton, the expansion rate of space itself, all appear to be calibrated with such exquisite precision that they seem almost impossibly tailored for the existence of complex structures and conscious beings. The fine-tuning multiverse theory proposes that rather than accepting this incredible coincidence as mere luck or divine design, we should consider that perhaps countless universes exist simultaneously, each one operating with its own unique set of physical constants and laws, and that we naturally find ourselves in one of the rare universes where these constants happen to permit our existence. Simply because universes lacking the right conditions could never produce observers to wonder at their own improbability. This framework dissolves the paradox of our perfectly calibrated cosmos by suggesting that somewhere across the infinite landscape of possible universes, at least one must have the right combination of conditions to generate consciousness, and inevitably, we would find ourselves in exactly such a place. The mechanism at work here involves what physicists call selection bias, or the anthropic principle, a logical framework that explains how we could observe something that seems statistically improbable without resorting to supernatural explanation or accepting pure. Imagine standing in a vast cosmic library where every shelf contains a different universe, each with its own set of physical laws and constants, and you find yourself asking the most unsettling question possible. Why do I exist in this particular universe where life is even possible at all? The anthropic principle emerges from this profound observation, suggesting that we should not be surprised to find ourselves in a universe that permits our existence, because if it did not, we simply would not be here to observe it. This principle comes in two primary forms, the weak anthropic principle stating merely that our location in the universe is privileged simply because we observe it, and the strong anthropic principle asserting that the universe must have properties that allow conscious observers to develop within it at some stage. The psychological mechanism underlying this reasoning operates through a subtle cognitive filter where we tend to forget about all the universes where observers cannot exist, focusing instead only on the one universe we inhabit, where the fundamental constants align so precisely that chemistry becomes possible, stars forge elements, and eventually consciousness emerges from the dust of dead stars. We observe the fine-tuning of physical constants with wonder, yet the anthropic principle suggests that this wonder itself contains a kind of circular logic, for if the constants were different, we would not be here to marvel at their precision. This perspective has normalized the idea that our astonishment at cosmic coincidence might be nothing more than a selection bias in consciousness itself. a profound reframing of how we understand our relationship to the fabric of reality, and whether the appearance of design in the universe reflects actual design or merely our inevitable position within the particular branch of existence that permits beings such as ourselves to contemplate the question. Imagine a universe that does not simply exist in static form across infinite space, but rather cycles through endless iterations of birth, expansion, contraction, and rebirth, with each cycle potentially spawning variations of itself that branch into parallel realities, creating what physicists call the cyclic multiverse model. This theory proposes that our universe is not a singular, one-time event that began with the Big Bang and will eventually end in heat death or the Big Rip, but rather one iteration in an eternal sequence of cosmic cycles, where each universe completes its lifespan and gives rise to the next, potentially with different physical laws, constants, and initial conditions than the one before it. The mechanism that drives this cyclical behavior operates through the mathematics of string theory and cosmological models that suggest the universe undergoes phases of expansion and contraction, where gravity eventually overcomes the outward momentum of space itself, causing everything to collapse inward until the density and pressure become so extreme that a new Big Bang emerges from the ashes of the previous cycle. What makes this concept particularly compelling to contemplate as consciousness drifts towards sleep is the profound implication that time itself becomes cyclical rather than linear, that history does not march toward a final destination, but instead spirals eternally through variations and repetitions, with each universe potentially slightly different from the last, creating infinite opportunities for different configurations of matter, energy, and the fundamental forces that govern existence. The cyclic multiverse model has maintained its theoretical credibility despite the challenges in finding observational evidence specifically, because it elegantly resolves several deep cosmological puzzles simultaneously, such as the problem of infinite regression in causality and the question of what preceded the Big Bang by Sugges. Imagine a cosmos that does not begin with a single explosive moment, but rather emerges from the collision of two vast, multidimensional membranes floating through a higher dimensional space, and you have entered the realm of the Ekpyrotic universe theory, a framework that challenges our most fundamental understanding of cosmic origins and infinity itself. Proposed by physicists including Paul Steinhardt and Neil Turok in the early 2000s, this theory suggests that what we perceive as the Big Bang was not the beginning of existence, but rather a violent encounter between two parallel three-dimensional worlds, or branes, existing in a five-dimensional bulk space that we cannot perceive directly. These branes, according to the theory, collide periodically in an eternal cosmic cycle, each collision triggering the expansion and evolution of a new universe, which gradually cools, becomes dark and empty, before eventually moving toward another catastrophic meeting that generates fresh creation and renewal. The word ekpyrotic itself derives from the ancient Greek term for conflagration or burning up, evoking the violent, fiery nature of these collisions that supposedly reshape reality on the grandest possible scales. The psychological appeal of this model lies in its ability to answer questions that have haunted cosmology for decades. What happened before the Big Bang, and what happens in the infinite future, as it proposes an elegant cyclical solution where time has no true beginning or end, but rather follows an eternal rhythm of destruction and rebirth. Our minds naturally gravitate toward such frameworks because they resolve the troubling paradox of causation itself, offering a mechanism by which something can eternally exist without requiring a singular moment of divine or spontaneous creation. Imagine a quantum system existing in a pristine state of superposition, where all possible outcomes exist simultaneously in a delicate dance of probability waves, and then consider what happens the moment that system interacts with the larger environment around it. Quantum decoherence is the process by which this fragile quantum state collapses into classical reality, where superposition dissolves and only one definite outcome remains observable. When a quantum particle exists in isolation within a laboratory apparatus, it maintains its wave-like nature, existing in multiple states at once. But the instant it touches the thermal environment, absorbs a photon, or interacts with any external field or observer, the coherence of its quantum state degrades irreversibly. The mechanisms driving this degradation are fundamentally about information leakage, where the quantum information encoded in the superposition becomes entangled with the vast degrees of freedom present in the surrounding environment, effectively hiding that information from direct observation and measurement. This is not a mysterious collapse or conscious observation effect as once theorized, but rather a natural consequence of thermodynamics and the second law, where isolated systems inevitably increase their entropy through interaction with everything else. What makes quantum decoherence conceptually fascinating is that it explains why we never observe the quantum world directly in our everyday lives, why macroscopic objects do not exist in superposition, and why the universe appears fundamentally classical to our senses despite being constructed from quantum foundations. It persists as a dominant explanation in physics because it provides a mathematically robust framework for understanding the quantum to classical transition without requiring observer consciousness or mysterious wave function collapses. Yet we have normalized the strangeness of living in a universe where really. Imagine standing at a threshold where reality itself branches into infinite versions of you, each one experiencing a subtly different outcome of the same moment, and this is the essence of wave function splitting, a concept that emerges naturally from the many worlds interpretation of quantum mechanics, where every quantum event that could result in multiple outcomes actually does result in all outcomes simultaneously. With the universe dividing itself to accommodate each possibility so that when you measure an electron's spin or observe the path a photon takes through a double slit, you are not collapsing a single wave function into one definite result, but rather triggering a split in the fabric of reality itself where both or all possible outcomes occur, each in their own branch of an ever-expanding multiverse. The psychological mechanism underlying our acceptance of this idea rests partly on the seductive elegance of it, because wave function splitting solves a persistent problem in quantum mechanics that has troubled physicists for over a century: the measurement problem, the troubling fact that quantum systems exist in superposition, in all possible states at once, until someone observes them, at which point they seem to snap into a single definite state. And many worlds' interpretation eliminates this uncomfortable observer dependence by simply declaring that no collapse occurs at all, that every possible outcome happens, and the appearance of a single definite outcome is just an illusion created by the fact that your consciousness is confined to one particular branch, while all the other branches continue existing independently where your other selves are having their own experiences. We have normalized this concept despite its profound weirdness, because it emerges logically from the mathematics of quantum mechanics without requiring any additional assumptions or unexplained mechanisms, unlike interpretations that invoke mysterious C. Imagine standing in a darkened room where a single quantum coin is about to be flipped, and as you watch, something remarkable happens. The universe itself branches into two distinct realities, one where the coin lands heads and another where it lands tails, and in each of these branching worlds, you experience a different outcome as your consciousness follows one particular path while simultaneously, in an equally valid sense, you also experience the other path in a parallel version of yourself that is just as real and just as aware as the version you identify with in this moment. This is the essence of Hugh Everett's relative state interpretation, proposed in 1956, which suggests that quantum superposition, that strange state where particles exist in multiple conditions simultaneously until observed, does not collapse into a single reality when measured, but instead causes the entire universe to split into multiple branches where every possible outcome occurs in its own separate world. The mechanism underlying this idea emerges from a profound logical consistency. If quantum mechanics truly describes all of physical reality without exception, then it must also describe the measuring devices and the observers themselves, which means that when you measure a quantum system, you and your measuring apparatus become entangled with that system and enter a superposition of states where in one branch you observe heads while in another branch you observe tails. With both branches being equally real and equally part of the universal wave function that never actually collapses, but eternally branches into new realities with each quantum interaction. What makes this theory persist despite its almost incomprehensible implications is that it eliminates the measurement problem entirely by refusing to treat observation as something special or magical that fundamentally changes reality, instead proposing that everything that can happen does. Imagine a universe so young and violent that entire regions of space expand at wildly different rates, each pocket inflating according to its own whims and quantum fluctuations, creating an eternal cascade of bubble universes that never quite settle into uniformity. This is the essence of chaotic inflation, a theoretical framework that emerged from the work of physicist Andrei Linde in the 1980s, proposing that the inflationary expansion of space itself was not a single, orderly event, but rather a chaotic, turbulent process occurring simultaneously across countless domains. In this model, the scalar field driving inflation does not smoothly decay everywhere at once. Instead, it fluctuates randomly from place to place, meaning some regions finish inflating while others continue expanding at accelerated rates, generating new bubble universes within the expanding whole. The mechanism underlying this vision relies on quantum mechanics at the grandest scales, where uncertainty is not merely an inconvenience but a fundamental feature of reality that seeds variations across space, causing inflation to end at different times in different locations, each spawning its own separate universe with potentially different physical constants and laws. What makes chaotic inflation psychologically compelling is how it transforms our conception of the Big Bang from a singular, coordinate event into an ongoing, fractal process still happening in regions we can never observe, suggesting that universe creation might be perpetual and distributed rather than ancient and centralized. Despite lacking direct observational evidence and existing in the realm of pure theoretical speculation, chaotic inflation has persisted in cosmological discourse because it elegantly solves certain problems inherent to simpler inflationary models, and because it naturally incorporates the multiverse concept, which has become increasingly normalized within theoretical physics. Imagine the universe as an enormous, unstable field of energy suspended in a state of false equilibrium, like water heated beyond its boiling point, yet somehow remaining liquid through sheer circumstance and improbable balance. Bubble nucleation describes the process by which small regions of space spontaneously transform from one quantum state into another, creating expanding spheres of new reality that propagate outward at nearly the speed of light, fundamentally altering the laws of physics wherever they spread. In the earliest moments after the Big Bang, as the universe cooled from incomprehensible temperatures, the fundamental fields governing particles and forces existed in what physicists call a false vacuum state, a condition of apparent stability that was not actually the lowest energy configuration available to nature. Within this framework, quantum fluctuations at the microscopic level occasionally generated pockets of true vacuum, the genuine ground state of lower energy, and these pockets would spontaneously nucleate and expand as bubbles, converting everything in their path into a new universe with potentially different physical constants and particle properties. The mechanism operates through quantum tunneling, whereby particles and fields can transition through energy barriers that should theoretically be impassable, creating these nucleation sites seemingly from nothing, regions of altered reality spreading outward and consuming the false vacuum around them. What makes bubble nucleation conceptually fascinating is that it suggests our own universe may be merely one bubble among countless others, a local pocket of physics surrounded by expanding bubbles of different realities, all nucleating and expanding simultaneously in an eternally inflating cosmic foam. Imagine our universe existing in a state that appears stable, yet fundamentally isn't, a precarious bubble of existence suspended in a quantum field that could, at any moment, spontaneously shift into a lower energy state. And when that happens, a sphere of annihilation would expand outward at the speed of light, obliterating everything within its path without warning or mercy. This is the concept of false vacuum decay, a theoretical scenario where the quantum fields that comprise reality itself occupy what physicists call a false vacuum, a state of apparent stability that is merely a local minimum in the vast landscape of possible quantum configurations. The mechanism works like this. In quantum field theory, the universe's fundamental fields exist in an energy state, and just as a ball rolling downhill will eventually reach the lowest possible point, these fields theoretically want to settle into their true ground state, their absolute lowest energy configuration, yet they might currently be trapped in a shallow valley, a false minimum, where they have remained for billions of years, because the probability of quantum tunneling through the energy barrier to reach the true minimum is extraordinarily remote. However, given enough time, a random quantum fluctuation could seed a bubble nucleation event somewhere in the cosmos, creating a pocket of true vacuum that would expand at relativistic speeds, transforming all the physical laws and constants within it into new values incompatible with the existence of atoms, stars, and life as we understand it. What is particularly striking about this theory is how we have intellectually normalized the possibility that our entire universe might simply cease to exist through no fault of our own, that the fundamental ground upon which all reality stands might be an illusion of stability. And yet we continue our daily lives with the understanding that this cosmic catastrophe remains theoretically possible. Imagine standing in an infinite garden where every possible flower that could ever exist blooms simultaneously across countless unseen fields. And the cosmic landscape theory suggests that our universe is merely one small plot within this incomprehensibly vast arrangement of mathematical possibilities. String theory, one of physics' most ambitious frameworks, predicts that the fundamental laws of nature can take on many different forms depending on how the extra dimensions of space curl up and fold upon themselves. And these different configurations would each produce a universe with its own unique set of physical laws and constants. The cosmic landscape itself is thought to contain somewhere between 10 to the power of 500 different possible universes, each one a distinct realization of how reality could be structured, each with electrons that might be slightly more massive or gravity that might work at different strengths. When physicists contemplate this landscape, they are essentially describing a multidimensional terrain where each valley and peak represents a different possible universe configuration, and our own universe simply happens to occupy one particular location on this vast and unimaginably complex terrain. The psychological mechanism that makes this theory compelling despite its staggering scope is our human tendency to apply familiar geographical metaphors to abstract mathematical spaces, transforming an equation into a mental map that feels somehow graspable. We find comfort in the notion that our universe, with all its apparent fine-tuning and improbable constants, is not uniquely special, but rather one instance among countless others, which paradoxically makes our particular existence feel less lonely even as it becomes infinitesimally smaller. Imagine, as you drift towards sleep, that the universe you inhabit is not a three-dimensional space floating through an empty void, but rather a thin membrane stretched across a higher-dimensional landscape, much like a sheet of fabric suspended in an invisible room whose walls you cannot see. M-theory proposes that what we perceive as fundamental particles and forces are actually tiny vibrations occurring on these membranes, called branes, and that our reality represents just one such membrane among countless others floating in a higher dimensional space known as the bulk. The theory emerges from the mathematical framework of string theory, where instead of point particles, everything consists of vibrating strings, and these strings require extra dimensions beyond the four we know to achieve mathematical consistency. What makes M-theory particularly fascinating is its suggestion that these membranes can collide, interact, and even vibrate in ways that create entirely separate universes with their own distinct physical laws. The human mind tends to organize unknown phenomena by drawing parallels to familiar objects, so we imagine membranes as sheets, branes as extended objects, and dimensions as directions we can somehow traverse, yet the actual mathematics describes something far more abstract and alien to our everyday intuition. We have normalized the concept of invisible parallel universes floating in higher dimensions, despite these ideas existing at the very edge of what modern physics can even theoretically test, and we accept that entire realities might exist layered beside our own with no possibility of direct observation or verification. This persistent acceptance of such radically unfamiliar concepts without immediate sensory evidence reveals how human consciousness stretches to accommodate abstract mathematical beauty and theoretical elegance, finding comfort in the idea that reality is stranger and more interconnected than our limmy. Imagine standing before a vast cosmic mirror where everything you perceive, every star, every atom, every thought contained within your mind, is not fundamentally three-dimensional, but rather a projection cast from a two-dimensional surface existing at the outer edge of the universe itself. This is the essence of the holographic multiverse theory, a concept emerging from theoretical physics that suggests our entire reality, along with countless other realities populating the multiverse, might be encoded as information on distant boundary surfaces, much like holograms rendered from flat data into seemingly solid three-dimensional form. The theory originates from the work of physicist Juan Maldacena in the late 1990s, building upon ideas about black hole thermodynamics and the fundamental nature of spacetime itself, proposing that a gravitational universe existing in higher dimensions could be completely equivalent to a quantum field theory existing on its lower dimensional boundary. What makes this concept psychologically compelling is its elegant resolution of certain paradoxes in physics, while simultaneously suggesting that multiple universes could all be holographic projections from shared or separate boundary conditions, each universe equally real and equally illusory depending on one's perspective. The mechanism that drives this idea forward in theoretical circles is its remarkable explanatory power, offering solutions to problems concerning black hole information loss and providing mathematical frameworks that reconcile quantum mechanics with general relativity. Yet despite possessing genuine scientific grounding and support from legitimate researchers, the holographic multiverse remains profoundly counterintuitive to our embodied experience, and we have somehow normalized the existence of a theory suggesting that consensus reality itself might be nothing more than information projected from distant cosmic surfaces, excepti. Imagine standing in a room where the walls themselves contain all the information needed to describe everything happening in the space before you, as though the interior and the boundary exist in perfect correspondence with each other despite their apparent separation and dimensionality difference. This is the essence of the AD-SCFT correspondence, a remarkable mathematical relationship discovered by Juan Maldacena in 1997 that suggests a five-dimensional space with a peculiar curved geometry called anti-de Sitter space can be completely equivalent to a four-dimensional quantum field theory that exists only on its boundary surface. The theory proposes that these two seemingly different descriptions of reality are not merely similar approximations, but are instead two entirely different ways of expressing the exact same physical system, much like how a hologram contains all the information of a three-dimensional object encoded on a two-dimensional surface. This duality emerged from string theory research and has become one of the most profound and unsettling insights in theoretical physics, because it suggests that three-dimensional volume and its contents might be nothing more than a projection or encoding of information residing on a lower dimensional boundary, fundamentally challenging our intuitive understanding of what space and dimension actually are. The psychological mechanism operating here involves our deep-seated need to find unity and elegance beneath apparent diversity, and the fact that such radically different mathematical frameworks could describe identical physics appeals to our sense that nature operates according to some hidden symmetry principle. We have normalized this extraordinary concept by incorporating it into countless research programs, quantum gravity investigations, and black hole studies, treating it as an established tool rather than the conceptually revolutionary assertion that bulk spacetime might. Imagine a particle encountering a barrier it should not be able to cross according to classical physics, yet somehow appearing on the other side anyway, having passed through the very wall that seemed to block its path completely. This phenomenon, known as quantum tunneling, occurs at the subatomic level, where particles behave according to probabilistic wave functions rather than deterministic trajectories. And this peculiar behavior has led some theoretical physicists to propose that tunneling events might not merely represent particles passing through barriers, but rather particles crossing into adjacent parallel universes where those barriers do not exist or are fundamentally different in their properties and composition. The quantum tunneling universe theory suggests that when a particle encounters a potential barrier that would require energy it does not possess, rather than being reflected back as classical mechanics would predict, the particle's wave function allows for a probability that it has tunneled into a neighboring reality where the conditions are such that it can exist on the other side of that barrier without violating conservation laws. This mechanism operates on the principle that quantum systems exist in superposition until measured, and that this superposition might extend across multiple dimensional configurations or parallel universes simultaneously. What makes this theory particularly compelling yet difficult to verify is that tunneling events happen constantly at quantum scales, in semiconductor materials, in nuclear decay, and in the very mechanisms that power stars, Yet we observe these events without ever directly confirming whether particles are genuinely passing through barriers or slipping sideways into adjacent universes where those barriers have different properties or do not exist at all. Imagine a universe that has existed for an incomprehensibly long time, stretched out across billions upon billions of years, gradually cooling toward a state of absolute equilibrium where nothing changes and no energy remains available to create structure or complexity. In such a universe, something profoundly strange becomes possible. The random fluctuations of particles in the void could theoretically arrange themselves, by pure chance, into the exact configuration necessary to create a conscious mind, complete with memories and thoughts, existing for only a brief moment before dissolving back into chaos. This hypothetical consciousness is called a Boltzmann brane, named after the 19th century physicist Ludwig Boltzmann, who first considered how statistical mechanics might produce such improbable arrangements from nothing but probability and time. The troubling implication of this concept is that in an eternally expanding universe, far more of these spontaneously assembled minds should exist than minds like ours, born from the slow accumulation of matter and energy following the Big Bang, which means the philosophical paradox emerges that we should statistically expect to be one of these random fluctuations rather than the product of natural evolution in an ordered universe. The mechanism underlying this unsettling possibility rests upon the understanding that given enough time, any possible arrangement of particles, no matter how unlikely, will eventually occur through pure statistical chance. And a sufficiently complex arrangement of particles could theoretically produce subjective experience and consciousness without any preceding structure, history, or causal chain. Yet despite the mathematical validity of this argument, physicists continue to work on cosmological models because accepting the Boltzmann brane hypothesis would render all observation and reasoning meaningless, since our thoughts and memories would be equally likely to be. Imagine a cosmos not as a single unified expanse, but as an enormous quilt of disconnected regions, each one a distinct universe with its own physical laws, fundamental constants, and dimensional architecture, stitched together at their edges in ways we cannot directly observe or traverse. The patchwork multiverse theory proposes that our universe is merely one tile in an infinite tapestry, where neighboring regions operate under completely different rules, where the speed of light might be faster or slower, where gravity pulls with different intensities, or where the very number of spatial dimensions varies from patch to patch. Each region formed perhaps through quantum fluctuations in a primordial vacuum, each bubble nucleating independently and settling into its own unique configuration of physical laws before expanding outward eternally. The boundaries between these patches remain forever sealed from our perspective, causally disconnected from our domain, meaning we will never witness the strange physics occurring just beyond our cosmic horizon. What makes this concept particularly compelling is how it elegantly addresses the fine-tuning problem, the troubling observation that our universe's constants seem improbably calibrated to allow for stars, planets, and ultimately life itself. Rather than requiring an improbable cosmic accident or invoking divine design, the patchwork model suggests that countless other patches simply failed to produce observers because their laws were incompatible with complexity and consciousness, making our own apparent fine-tuning an inevitable consequence of observation selection bias rather than miraculous coincidence. We inhabit one patch precisely because we could not exist in any other, and this deeply unsettling idea has become woven into modern cosmological thinking, reshaping how physicists interpret the universe's deepest mysteries despite the mathematical frameworks remaining speculative and untested. Imagine standing at the edge of the observable universe, a boundary defined not by some cosmic wall, but by the finite speed of light in the age of the cosmos itself, what astronomers call the Hubble volume, and imagine that within this sphere of space that contains all the galaxies and matter we can ever perceive, there exists another identical sphere somewhere far beyond our ability to see, containing an exact replica of every atom, every star, every conscious being, arranged in precisely the same configuration as our own observable universe. This concept emerges from the mathematical properties of infinite space combined with the finite number of possible arrangements of matter, a principle sometimes called recurrence or eternal recurrence on a cosmic scale. Within an infinitely vast universe with only a finite number of distinct configurations that matter can assume, statistical probability dictates that eventually, somewhere in that endless expanse, the exact same arrangement of atoms must repeat, creating not just one duplicate of our Hubble volume, but theoretically infinite duplicates scattered throughout eternity. The mechanism behind this persistence involves our acceptance of infinity itself and the limitations of variation in a universe governed by quantum mechanics, which restricts possible states to discrete rather than continuous values, meaning that while the universe is incomprehensibly vast, the number of unique configurations it can manifest remains finite, however enormous that number might be. What makes this concept persist in serious cosmological discourse, despite its unsettling implications, is not mere speculation, but rigorous mathematical logic applied to eternal inflation theory, where space continuously generates new bubble universes in an unending process, and given enough time and space, the laws of probability transform the merely possible into the inevitable. Consider the simple geometric proposition that if space itself is infinite, extending endlessly in all directions without boundary or edge, then the volume contained within that space becomes so incomprehensibly vast that the probability of certain arrangements of matter occurring becomes not merely possible but inevitable, and in fact must occur infinite times over. This principle, sometimes called the infinite universe hypothesis, suggests that if you were to travel far enough in any direction, you would eventually encounter another version of this planet, another solar system arranged precisely as ours is, and indeed another you, reading these same words in another room of another house in another galaxy, all perfectly replicated by the sheer mathematics of probability and infinite space. The logical mechanism underlying this idea stems from a straightforward mathematical truth. When you have infinite opportunities for something to happen, and that something has any probability greater than zero, it will happen infinite times, and when you multiply the number of possible arrangements of particles in space by infinity itself, every possible arrangement must occur somewhere within that expanse. We find ourselves oddly comfortable with this notion, despite its mind-bending implications, perhaps because we have normalized the concept of infinity through mathematics and cosmology, treating it less as a philosophical paradox and more as a neutral fact of existence, a mere consequence of the universe being what it appears to be rather than a conceptual crisis worth dwelling upon. The infinite space principle thus transforms our understanding from one where our existence is rare and unique to one where our existence is actually inevitable and repeated endlessly. A shift so profound in its implications that we rarely pause to consider what it truly means for our sense of significance or individuality in a cosmos of infinite replication. Imagine standing at the very edge of physics, where time itself becomes questionable and the universe ceases to be a collection of objects moving through space, but rather becomes a single, unified whole without beginning or end. This is where the Wheeler-DeWitt equation lives, conceived in the 1960s by physicists John Wheeler and Bryce-DeWitt, as they grappled with one of the most profound contradictions in modern science, the complete incompatibility between quantum mechanics and general relativity. In our everyday experience, we understand the universe through these two frameworks, yet they fundamentally disagree about how reality operates at the smallest and largest scales. The Wheeler-DeWitt equation represents an attempt to merge these warring theories into something called quantum gravity, and it does this by treating the entire universe as a single quantum object, a wave function that encompasses all of space and time itself. What makes this equation so philosophically disorienting is that it contains no time derivative, meaning time does not appear as a fundamental variable within it, suggesting that time as we experience it may be merely an emergent property, an illusion that arises from the way we observe the universe rather than something that fundamentally exists. Physicists working with this equation have come to accept that the wave function of the universe simply exists, unchanging and eternal, with all possible configurations of reality superimposed upon one another in a kind of cosmic probability cloud. This strange acceptance persists despite the fact that it contradicts our most basic intuitions about causality, change, and the very notion of events unfolding sequentially. Yet we have normalized this bewildering framework because it represents our best mathematical attempt to describe the universe at its most fundamental level. Imagine standing at the edge of a vast, featureless plane that extends infinitely in all directions, and as you look upward, the sky gradually transforms into the ground beneath your feet, curving seamlessly without any visible seam or junction, as if the universe has folded itself into a shape so perfectly smooth that the distinction between beginning and ending simply ceases to exist. This is the essence of the no-boundary proposal, a concept developed by James Hartle and Stephen Hawking in the mid-1980s, which suggests that the universe has no actual boundaries in space or time, neither a starting point nor an endpoint, but rather exists as a closed, finite system that curves back upon itself in the mathematical fabric of spacetime. The psychological appeal of this idea lies in its elegant resolution of a deeply troubling question that has haunted cosmologists and philosophers alike, the question of what came before the beginning. For if there is no boundary, there is quite literally nothing that exists beyond the edge, because there is no edge at all. The mechanism through which this concept operates relies on a profound shift in how we understand time itself, transforming it from a linear arrow shooting forward from some distant moment of creation into a dimension much like the spatial dimensions we navigate daily, one that curves and closes back upon itself like a circle, creating what physicists call imaginary time. Within this framework, the universe becomes self-contained and complete, requiring no external cause, no divine spark, no moment of ignition, because causality itself becomes a meaningless concept at the boundary of existence when there is no boundary to speak of. We have gradually normalized this strikingly counterintuitive notion because it offers something profound, a way to silence the infinite regress of why questions that otherwise seem to have no satisfying answer, and in doing so, it transforms a philos. Imagine standing at the very edge of existence itself, at a moment so infinitesimally small and so profoundly strange that the ordinary rules of physics begin to dissolve into something altogether different. Something where time and space lose their familiar meaning and become fluid, negotiable, almost dreamlike in their properties. This is the conceptual landscape where the Hartle-Hawking state attempts to make sense of what came before the Big Bang, or rather, whether the very notion of before even makes coherent sense. James Hartle and Stephen Hawking proposed in 1983 that the universe might exist in a particular quantum state at its very beginning, one where the boundary conditions of spacetime itself are defined not by some external creator or initial singularity, but by the mathematics of quantum mechanics applied to gravity itself. In their formulation, time does not simply begin at some arbitrary instant with all the force of a thunderclap. Instead, it emerges gradually, asymptotically, from a state that is fundamentally quantum mechanical and utterly foreign to our intuitive sense of causality and sequence. The proposal suggests that in the earliest moments, the distinction between space and imaginary time becomes almost meaningless, that space and time are equally fundamental and interchangeable at these scales, creating what they termed the no-boundary proposal, where the universe has no edge, no beginning point, no creation moment that requires explanation from outside physics itself. The conceptual mechanism underlying this state rests upon the remarkable observation that if one applies quantum mechanics to the entire universe as a closed system, one can imagine time behaving like an additional spatial dimension near the singularity, with the universe's history forming a kind of four-dimensional sphere without boundaries, much as the surface of Earth has no edge despite being finite. Imagine standing at the edge of what physicists call the quantization hierarchy, where the very act of observation and measurement has itself become something that requires mathematical treatment, something that needs to be quantized in turn. In the traditional framework of quantum mechanics, we quantize fields, converting classical continuous waves into discrete packets of energy called quanta, particles that behave according to probabilistic rules rather than deterministic ones. Then, when we move into quantum field theory, we quantize those fields themselves, treating the creation and annihilation of particles as fundamental operations governed by operators in a mathematical space. But third quantization pushes this process to its logical extreme, proposing that the wave function itself, that mysterious mathematical object which describes the probability of finding a particle in any given state, should become subject to quantization, transforming it from a classical field into a quantum field in its own right. This creates a peculiar recursive layer where the probability itself becomes quantized, introducing new particles and new uncertainties into domains we thought we had already understood. The mechanism behind this strange necessity emerges from attempts to reconcile quantum mechanics with general relativity, to build a theory of quantum gravity where spacetime itself becomes uncertain and fluctuates at the smallest scales. When you try to quantize gravity, treating the geometry of spacetime as something subject to quantum rules, you find yourself dealing with infinities and mathematical inconsistencies that refuse to disappear through standard renormalization techniques. Third quantization offers one potential escape hatch, a way to push the problem up another level of abstraction, suggesting that perhaps the entire wave function of the universe itself is subject to quantum fluctuations, creating multitudes of parallel configurations. Imagine the universe itself as a living system capable of creating smaller universes within itself, much like a parent organism producing offspring that inherit certain characteristics while developing their own unique properties. And this concept, known as the theory of baby universes, emerges from some of the most sophisticated mathematical frameworks in modern theoretical physics, particularly from the work of physicists like Smolin and his fecund universe hypothesis. The mechanism behind this idea rests on the possibility that when a black hole forms and collapses into a singularity, it might not simply disappear from our universe, but instead create a tunnel or bridge that leads to an entirely new and separate universe, complete with its own set of physical constants, its own laws of nature, and its own potential for stars, planets, and perhaps even life. This process would be utterly invisible to us because the new universe would be causally disconnected from our own, sealed off behind the event horizon of the black hole, meaning no information could ever travel back to inform us of what transpired or what came into being. What makes this theory particularly compelling to physicists is not just its mathematical elegance, but also its potential to address some of the deepest questions about why our universe has the specific physical constants it does, suggesting that if universes can reproduce and spawn baby universes, then the ones most capable of producing black holes and thus creating offspring universes would naturally become more prevalent across the multiverse. A kind of cosmic natural selection that might explain the apparent fine-tuning of our own physical laws. Yet despite the sophistication of this framework and its grounding in general relativity and quantum mechanics, we persist in treating it as speculation rather than established fact, partly because we can never observe or verify these baby universes, but also because our me. Imagine for a moment that the fabric of spacetime itself contains tiny tunnels, invisible shortcuts woven through the very structure of reality, passages that could theoretically connect distant points in the universe or even separate universes themselves without the traveler having to traverse the space between them. And this concept, far from being pure fantasy, emerges directly from Einstein's field equations as a legitimate mathematical solution that physicists call Einstein-Rosen bridges. Though they remain purely theoretical and likely unstable. The real-life situation is that modern physics has identified these mathematical solutions in general relativity, meaning the equations that describe how gravity warps spacetime do technically permit the existence of wormholes. And some theoretical physicists have spent decades exploring whether such structures could actually form, persist, or be traversable under any physically realistic conditions. Examining questions about whether exotic matter with negative energy density could prop them open, or whether quantum effects might naturally create and destroy them on microscopic scales. The psychological mechanism driving our fascination with wormholes stems from something deeply human: the desire to transcend limitation and distance, the yearning for shortcuts through an otherwise vast and seemingly impenetrable cosmos, and the comfort found in knowing that reality's mathematics leaves room for such possibilities even if we cannot yet prove they exist in any practical form. What persists despite its speculative nature is how thoroughly wormholes have become normalized in scientific discourse, how they appear in peer-reviewed papers alongside observations and experiments, and how they've transformed from pure mathematical curiosities into serious subjects of inquiry, giving us permission to wonder about connections between distant regions or alternate universes without feeling we've abandoned low. Imagine a universe that gives birth to new universes, each one slightly different from its parent, each one carrying forward the fundamental constants and laws that shaped its predecessor. And this is the essence of Smolin's fecund universes hypothesis, a theory that reframes the entire cosmos not as a singular, static creation, but as a reproductive system operating across scales of time and space almost impossible to comprehend. Smolin, a theoretical physicist at the Perimeter Institute, proposed in the 1990s that universes might create daughter universes through their black holes, and that these offspring universes would inherit slightly modified versions of their parent universe's physical laws, much the way children inherit traits from their parents, but with variations that accumulate across generations. The mechanism rests on a simple but profound idea. When a black hole forms and collapses into a singularity, rather than representing a dead end, it might actually tunnel through to a new region of spacetime where entirely new physical laws govern reality, a kind of cosmic reproduction that occurs within the very heart of matter's most extreme states. This theory elegantly addresses a fundamental puzzle in cosmology, the apparent fine-tuning of our universe's constants that seem precisely calibrated to allow for stars, planets, and ultimately life itself. By suggesting that natural selection operates on a cosmic scale, where universes producing the most black holes, and therefore the most offspring, would naturally come to dominate the multiverse's population over countless generations. The psychological appeal of this framework lies partly in its explanatory power, offering a mechanism that transforms incomprehensible coincidence into comprehensible process. Yet it persists as a serious consideration in theoretical physics despite being essentially untestable through any conventional observational means, existing in a realm where math. Imagine a universe that gives birth to new universes through the collapse of black holes, each offspring slightly different from its parent, each carrying forward the fundamental constants and physical laws with minor variations inherited like genetic material across a cosmic family tree. This is the essence of cosmological natural selection, a theory proposed by physicist Smolin in the 1990s, which suggests that universes themselves undergo a process remarkably similar to biological evolution, where successful universe-creating configurations persist and proliferate while unsuccessful ones fade away. The mechanism operates on a scale almost incomprehensibly vast, where every black hole might represent not an ending but a genesis event, a doorway through which a new universe emerges into its own separate spacetime, carrying forward the physical constants from its parent universe with slight quantum fluctuations and modifications that make each offspring universe subtly unique. The psychological appeal of this theory lies in its elegant unification of two seemingly disparate domains: the organic complexity we observe in living systems and the fundamental question of why our universe appears so finely tuned for the emergence of complexity in consciousness. We find comfort in recognizing patterns we already understand applied to the deepest mysteries of existence, in the notion that the universe itself obeys principles we have observed in nature for centuries. The theory persists in cosmological discourse despite its challenging implications and lack of direct empirical falsifiability, partly because it offers an alternative to the anthropic principle by suggesting that fine-tuning emerges naturally through selection rather than chance or divine design. Imagine standing at the edge of infinity, where the end of one universe becomes the beginning of another, not through catastrophe or collision, but through a gentle mathematical transformation that renders the vastness of space and the infinity of time as nothing more than a perspective shift. This is the essence of conformal cyclic cosmology, a theory proposed by physicist Roger Penrose that suggests our universe exists not as a singular, isolated event stretching infinitely backward and forward in time, but rather as one infinite cycle in an endless sequence of universes, each one arising from the infinite future of the previous age. The theory works through an elegant mathematical concept called conformal rescaling, which allows physicists to take the infinitely large and infinitely far and reinterpret them as finite and near by simply changing how we measure distances and time, much like adjusting the zoom level on a cosmic map. In this framework, what we perceive as the infinite future of our universe, where all stars have died and the cosmos has expanded beyond recognition, becomes mathematically identical to the infinite past and initial conditions of a new universe, creating a seamless transition that the theory calls an eon. Each eon contains its own Big Bang, its own history of stars and galaxies and civilizations, and its own ultimate fate as everything spreads into infinite emptiness. The psychological appeal of this model rests partly on its elegant symmetry and partly on humanity's deep discomfort with true endings and absolute beginnings, offering instead a cyclical comfort where nothing is ever truly lost or created from nothing. Despite lacking direct observational evidence and remaining speculative in nature, the theory persists in cosmological discourse because it addresses fundamental questions about causation and entropy while maintaining mathematical rigor, allowing scientists and dreamers alike to contemplate. Imagine standing at the edge of infinity, looking backward through time itself, only to discover that what lies ahead might be what once lay behind, a concept so profound, and yet so elegantly simple that it challenges everything we thought we understood about the beginning and ending of our universe. This is the essence of Penrose conformal cyclic cosmology, a theoretical framework proposed by physicist Roger Penrose, which suggests that the universe does not simply expand infinitely into a cold, dark void, but rather undergoes infinite cycles of expansion and rebirth, each cycle containing within it the infinite future of the previous one. The theory proposes that what we perceive as the infinite distant future of our current universe becomes, through a remarkable mathematical transformation called conformal rescaling, the infinite distant past of an entirely new universe, creating an endless chain of cosmic ages, each one complete and infinite in its own right, yet seamlessly connected to the ones before and after it. The psychological allure of this idea lies in its profound rejection of both absolute beginnings and absolute endings, offering instead a cyclical eternity where time flows forward eternally, yet somehow folds back upon itself in ways that challenge our conventional understanding of causality and sequence. What makes Penrose CCC particularly fascinating is how it addresses one of cosmology's deepest mysteries, the apparent fine-tuning of physical constants that make our universe habitable, by suggesting that information from previous universal cycles can influence the conditions of subsequent ones through Hawking radiation imprints and gravitational wave signatures. Yet despite its mathematical elegance and the considerable reputation of its proponent, the theory remains deeply controversial and largely untestable by current observational methods, persisting in the landscape of theoretical physics not because it has been proven, but imagine a cosmos that does not begin with a singular moment of infinite density and temperature, but rather unfolds from a collision between two vast, multidimensional surfaces moving through higher dimensional space, and you have glimpsed the essential architecture of the Steinhardt-Turok model, a theoretical framework that fundamentally reimagines how our universe might have originated and continues to evolve through cycles of expansion and contraction across incomprehensibly vast timescales. Proposed by physicists Paul Steinhardt and Neil Turok in the early 2000s, this Ekpyrotic model suggests that what we perceive as the Big Bang is not truly a beginning, but rather a collision event between two parallel universes or branes, which are lower dimensional surfaces embedded within a higher dimensional space called the bulk, and that our current period of cosmic expansion and cooling will eventually reverse, leading to a contraction, another collision, and the birth of another universe in an infinite cyclic pattern. The psychological mechanism underlying this model rests on humanity's deep discomfort with absolute beginnings and the concept of true nothingness, for we are creatures shaped by experiences where one thing always precedes another, where causation flows from past to future without interruption, and the notion that everything simply appeared from nothing violates this fundamental intuition about how reality must operate. What makes the Steinhardt-Turok model particularly compelling to contemporary cosmologists is that it elegantly sidesteps certain mathematical infinities that plague traditional Big Bang theory, while remaining consistent with observations of cosmic microwave background radiation and the large-scale structure of the universe. Yet we have somehow normalized the notion that our universe might be merely one collision in an eternal dance of branes, despite the profound metaphysical weirdness of infinite cyclic. Imagine a universe that expands and contracts in an endless cycle, like the breathing of some cosmic entity that has existed forever and will continue to exist forever, each exhale giving birth to a new Big Bang, and each inhale drawing all matter and energy back into a singularity before the cycle begins anew. This is the concept of oscillating universes, a theoretical framework that emerged primarily in the mid-20th century as physicists grappled with the fundamental question of what came before our universe began. In this model, our current expansion phase is merely one breath in an infinite respiratory cycle, and before our Big Bang there was a previous universe that collapsed, and before that another, stretching backward through infinite time without ever requiring a true creation moment or an absolute beginning. The psychological appeal of this theory lies in its elegant resolution of the creation paradox, for instead of asking the uncomfortable question of what caused the universe to exist, the oscillating model simply states that the universe has always existed in some form, perpetually cycling through phases of expansion and contraction. Each universe leaves traces and imprints upon the next through the remnants of its previous state, and in some formulations, information from earlier iterations might persist or influence the initial conditions of subsequent ones. What makes this theory particularly soothing to contemplate is how it eliminates the sense of absolute finality or absolute beginning, replacing catastrophic singularities with rhythmic patterns reminiscent of natural cycles we observe everywhere in nature, from the seasons to the orbits of planets to the beating of our own hearts. The oscillating universe persists as a compelling framework despite modern cosmological observations suggesting the universe will expand forever rather than contract, because it provides a kind of temporal symmetry and wholeness that appear. Imagine a cosmos that does not persist eternally in some fixed state, but instead cycles through infinite deaths and rebirths, each iteration following the same physical laws, yet arriving at entirely different configurations of matter and energy, and you have encountered the Phoenix universe concept, a theoretical framework that emerged primarily from the work of physicist Roger Penrose and his conformal cyclic cosmology hypothesis, which proposes that what we perceive as the infinite future of our universe is actually the infinite past of the next universe, creating an eternal sequence of cosmic eons that each contain within them the full history of expansion, matter formation, and eventual entropy. The mechanism underlying this theory rests on a mathematical observation about the nature of infinity and scale itself. For Penrose recognized that in an infinitely old and infinitely large universe with no boundaries, there exists a fundamental equivalence between the infinitely distant future of one universe and the infinitely remote past of another, since the infinite geometry at one end mirrors the infinite geometry at the other end. And this symmetry allows universes to chain together like beads on an endless string, each one dying into absolute cold death only to be reborn from what appears to be a new Big Bang. This concept persists within theoretical physics despite its counterintuitive nature, partly because it offers elegant solutions to certain cosmological puzzles, such as the unexpectedly low entropy state of the Big Bang and the distribution of supermassive black holes throughout our visible universe. Yet it remains almost entirely untestable and unfalsifiable through conventional observation, which means we continue to discuss and develop it as a legitimate branch of cosmological inquiry, even though we possess virtually no empirical pathway to confirm or deny its validity, creating a curious situation where mathematical beauty and low. Imagine the smallest possible scale of reality, far smaller than atoms or even the subatomic particles we can observe in laboratories, a realm where the very fabric of spacetime itself begins to behave in ways that challenge our intuitions about the nature of existence. At this quantum scale, the universe is not the smooth, continuous field that Einstein described, but rather a roiling, turbulent sea of virtual particles constantly erupting from and collapsing back into nothingness, a phenomenon physicists call quantum foam. This concept emerges from the marriage of quantum mechanics and general relativity, two pillars of modern physics that normally govern different scales of reality, but occasionally overlap in their predictions about what happens at the Planck scale, the smallest meaningful unit of distance and time in the universe. The quantum foam represents a solution to a profound problem. Quantum mechanics tells us that empty space cannot truly be empty because of the uncertainty principle, which forbids us from knowing both the energy and the time of existence of a particle simultaneously, meaning that in infinitesimally small intervals of time, particles can borrow energy from the vacuum itself, appearing and disappearing so quickly that we cannot detect them directly. These virtual particles, fluctuating in and out of existence at rates proportional to their mass and energy, create a seething landscape beneath reality's surface, a democratic chaos where every possible particle pair can briefly manifest before the universe's ledger demands they return to nothingness. What makes this theory particularly fascinating is how it persists and maintains credibility despite being fundamentally unobservable. For the quantum foam operates at scales so infinitesimally small that no conceivable experiment we could perform with our current or foreseeable technology could ever directly detect these fluctuations. Yet physicists continue to develop and ray. Imagine the smallest possible ruler you could ever create, one so impossibly tiny that it measures the fundamental grain of reality itself. And at this scale, something extraordinary occurs that challenges our deepest assumptions about what is solid, stable, and real. The Planck scale, named after physicist Max Planck, represents a length of approximately 1.6 times 10 to the negative 35 meters, a distance so infinitesimally small that it exists far beyond our ability to observe or measure directly. Yet at this threshold, quantum mechanics and general relativity collide in ways that suggest the fabric of spacetime itself is not smooth and continuous, but rather violently turbulent and chaotic. At these scales, the energy required to probe the universe reveals that empty space is not truly empty at all, but rather seethes with virtual particles that constantly pop into existence and annihilate themselves in accordance with the uncertainty principle, creating momentary fluctuations in the geometry of space and time that ripple outward with consequences we are only beginning to understand. The psychological weight of this concept emerges from the unsettling realization that, beneath everything we perceive as stable and orderly, there exists a realm of absolute disorder and uncertainty, where the very notions of position, momentum, and time become fundamentally unknowable. Yet this fundamental instability somehow gives rise to the ordered universe we inhabit, suggesting that chaos and structure are not opposites, but rather manifestations of the same underlying reality. We have normalized this profound weirdness by treating Planck scale fluctuations as a theoretical framework rather than a description of actual physical reality, allowing us to maintain our intuitive sense that the world operates according to comprehensible rules, even though the universe appears to be built upon foundations that are inherently and irreducible. Imagine a foam of existence so infinitesimally small and fleeting that it operates beneath the threshold of observation, where particles emerge from nothing and vanish back into nothing in spans of time so brief that our minds cannot truly grasp them. This is the realm of virtual particles, those ghostly entities that quantum mechanics tells us are constantly winking in and out of existence throughout all of space, and some physicists propose that each of these virtual particle pairs, in their momentary existence, might give rise to entire universes unto themselves. According to this interpretation, what we perceive as the vacuum of space is not empty at all, but rather teeming with an infinite cascade of virtual particle universes, each one a complete cosmos with its own physical laws and dimensions, sprouting into being and collapsing back into quantum uncertainty in timeframes so vanishingly small that they operate entirely outside the realm of causality as we understand it. The mechanism behind this concept emerges from the uncertainty principle itself, which fundamentally dictates that energy and time are complementary variables bound by an inverse relationship, meaning that for sufficiently brief intervals, particles can borrow energy from the quantum field and manifest as temporary matter, existing just long enough to satisfy the mathematical constraints of quantum mechanics before annihilating back into pure potential. These virtual particle universes would exist in a state of superposition, containing infinite variations of reality, infinite physical constants, infinite possibilities for life and consciousness, all simultaneously real and unreal until the moment they collapse back into quantum nothingness. And the peculiar thing about this framework is that we have become so accustomed to treating these mathematical abstractions as physically real entities that we rarely pause to consider how extraordinary this proposition AC. Imagine the seemingly empty space between particles, the void that appears to contain nothing at all. Yet according to quantum field theory, this vacuum is actually seething with activity at scales too small for us to directly perceive, a concept that begins to unravel our intuitive understanding of what emptiness truly means. The vacuum energy, sometimes called dark energy or the cosmological constant, is theorized to vary across different regions of space and potentially across different universes within the multiverse framework, suggesting that the fundamental energy density of nothingness itself is not uniform, but rather fluctuates based on unknown principles we have yet to fully comprehend. In our own universe, this vacuum energy appears to be driving the accelerated expansion of space itself, pushing galaxies apart at ever-increasing velocities. Yet in another region of the multiverse or across different pocket universes, this energy density might be dramatically higher or lower, creating universes with fundamentally different properties and physical laws. The psychological mechanism that allows us to accept this strange idea rests on our willingness to embrace mathematical consistency over intuitive reality, for the equations describing quantum fields seem to require that this vacuum energy exists and varies, and when mathematics proves more reliable than our senses, we learn to trust the abstract formulation rather than our immediate experience. We have normalized the notion that empty space contains infinite potential energy fluctuations, that virtual particles constantly materialize and annihilate within the void, and that these variations might explain why our universe has the particular constants and physical laws that it does, without fully grasping what any of this means in concrete terms. Imagine a perfectly balanced pencil standing on its sharpened point, theoretically capable of remaining upright indefinitely if the conditions were absolutely ideal. Yet in reality it must eventually fall in some direction, and once it falls, that broken symmetry becomes the defining feature of its new state. And this simple act of collapse from perfect balance into an asymmetrical configuration is the essence of what physicists call spontaneous symmetry breaking, a phenomenon that appears throughout the universe at every scale and temperature regime. In the early moments after the Big Bang, when the universe was infinitely hot and dense, all the fundamental forces existed in a unified, symmetrical state where electromagnetic force, weak nuclear force, and strong nuclear force were indistinguishable from one another, existing as a single symmetric whole with no preference for any particular direction or configuration. As the universe rapidly expanded and cooled, however, this perfect symmetry could no longer be maintained, and the system spontaneously collapsed into a lower energy state where the forces separated and differentiated, with the electromagnetic and weak forces branching away from their unified symmetry in what we now observe as distinct fundamental interactions. The psychological mechanism underlying our understanding of this phenomenon rests on the recognition that perfect symmetry, while theoretically elegant and seemingly more stable, is actually far more fragile and temporary than asymmetry, because any infinitesimal perturbation, any microscopic fluctuation or quantum uncertainty can tip a perfectly balanced system toward one outcome rather than another. What makes spontaneous symmetry breaking so profound is that the universe appears fundamentally indifferent to which direction the symmetry breaks, meaning that when a pencil falls, it has no preference for left or right, and when the electroweak symmetry broke, imagine the universe as an infinite ocean of energy, and within that ocean exist boundaries where everything changes abruptly, where the rules themselves transform without warning, much like water becoming ice or steam becoming water again. Phase transitions in the context of multiverse theory describe moments in cosmic history where the fundamental nature of reality undergoes a dramatic shift, where the forces that govern existence reorganize themselves into entirely different configurations, and these transitions are thought to have occurred repeatedly throughout the history of our universe and potentially across infinite parallel universes simultaneously. In the early moments after the Big Bang, the universe existed in an extremely hot, dense state where all fundamental forces were unified into a single force. And as the universe expanded and cooled, these forces began to separate sequentially, each separation marking a distinct phase transition, much like how a uniform liquid suddenly crystallizes into ordered patterns when cooled below a critical temperature. The electroweak phase transition, which occurred mere fractions of a second after the Big Bang, represented the moment when electromagnetism and the weak nuclear force split apart from their unified state, fundamentally altering the properties of elementary particles and the vacuum of space itself. What makes this concept psychologically gripping is the realization that reality as we understand it is not immutable or eternal, but rather the product of a specific configuration of forces that could theoretically shift again, that the very ground of existence we take for granted could transform into something utterly unrecognizable if the conditions were right. Yet we persist in our understanding of physics and cosmology despite the unsettling implication that our universe may simply be one particular phase among countless others, that what we perceive as the laws of nature might be as. Imagine the universe as a vast tapestry woven from countless quantum fields, each one vibrating at different frequencies and intensities across the fabric of spacetime. And within this tapestry, there exist regions separated by invisible boundaries called domain walls, which are essentially cosmic defects that emerge when a quantum field settles into different ground states in adjacent regions of space. These domain walls arise naturally from the physics of symmetry breaking, the same mechanism that gives particles their mass and defines the fundamental forces we observe, and they represent the energetic barriers that form at the interfaces where one vacuum state transitions abruptly into another, much like the boundary between regions of a magnetic material where the spin orientation flips in opposite directions. The concept emerged from theoretical physics in the 1970s as physicists contemplated what happens when a scalar field in the early universe undergoes a phase transition, creating domains of different quantum configurations, and the walls themselves would be thin but incredibly dense structures carrying enormous amounts of energy per unit area, potentially stretching across light years or even larger cosmic distances. What makes domain walls particularly intriguing within multiverse theory is that they could connect different pocket universes or distinct regions governed by different physical laws and constants, suggesting that our observable universe might border regions with fundamentally different properties, where gravity behaves differently or where the strength of electromagnetic forces bears no resemblance to what we measure in our own corner of existence. These structures would remain stable through the passage of eons unless they encounter other cosmic defects or unless quantum processes cause them to gradually decay. And the fascinating asymmetry lies in how these walls separate not merely different states of the same. Imagine the fabric of spacetime itself containing infinitesimally thin, one-dimensional defects that stretch across the entire universe, remnants from the earliest moments of cosmic inflation when the universe cooled and symmetries were broken in ways we still struggle to comprehend. These cosmic strings are theoretical structures so extraordinarily thin yet so incredibly dense that a single string the width of a proton would weigh as much as a mountain. And according to string theory and certain unified field theories, countless numbers of them could be woven throughout the multiverse, connecting different regions of space and time in ways that fundamentally alter the geometry of reality itself. The conceptual mechanism underlying cosmic strings emerges from phase transitions in quantum fields, similar to how water freezes into crystalline structures along fault lines, except occurring at energy scales billions of times higher than anything we can observe or recreate, leaving topological defects in the quantum vacuum that persist because they are energetically trapped states with no low-energy pathway to dissolution. These strings would create measurable gravitational lensing effects on light from distant galaxies, bend the cosmic microwave background radiation in characteristic patterns, and possibly serve as seeds around which galaxies themselves could accumulate and grow, making them not merely abstract mathematical curiosities, but potentially fundamental to understanding why our universe looks the way it does. What remains genuinely perplexing is how we have normalized the existence of these objects despite never directly detecting them, despite their existence resting on theoretical frameworks that remain unproven, and despite the profound strangeness of accepting that the universe might contain these one-dimensional scars running through it, invisible to us yet gravitationally real and influential, shaping the very cosmic web we inhabit. Imagine standing in a vast cosmic fabric that stretches infinitely in all directions, a tapestry woven from the fundamental threads of reality itself, and yet within this otherwise uniform expanse, there exist peculiar imperfections where the weave has gone subtly wrong, where the pattern breaks down into something rough and irregular and fundamentally different from the rest. These are texture defects in the multiverse, theoretical flaws, or irregularities in the quantum foam that underlies all existence, places where the smooth mathematical elegance of spacetime develops wrinkles and creases and distortions that should not logically occur according to our most refined equations. The theory suggests that during the earliest moments of cosmic inflation, when the universe expanded faster than the speed of light and stretched all quantum fluctuations to impossible scales, certain regions experienced slightly different conditions or cooling rates, causing the fabric of reality itself to settle unevenly, like wet concrete that dries with cracks and fissures. These defects would manifest as topological anomalies, cosmic strings, domain walls, or monopoles, structures that exist at the boundaries between different vacuum states, creating permanent scars in the texture of spacetime that persist even as the universe ages and expands. What makes texture defects conceptually fascinating is how they represent a kind of cosmic imperfection, a deviation from the pristine mathematical symmetry that physicists have long sought as the ultimate truth underlying all phenomena, yet we have come to accept that perfection itself might be impossible, that flaws and asymmetries are not signs of theoretical failure, but rather inevitable features of any real physical system. These defects would shape how galaxies form, how gravitational fields behave, and potentially how consciousness and observers emerge within the multiverse, meaning that the universe's texture, its foo. Imagine walking through the world of magnetism and noticing something profoundly asymmetrical, something that violates the elegant mirror image we see everywhere else in physics, and that asymmetry is the monopole problem, a puzzle that has haunted theoretical physicists for nearly a century. In electromagnetism, we encounter two fundamental types of charges, positive and negative, which can exist independently and in isolation, allowing us to study a single electron or proton in complete separation from its opposite. Yet magnetism behaves differently in a way that seems almost deliberately perverse, for whenever we examine any magnet, no matter how small or precisely we divide it, we always find both a north pole and a south pole together, bound in an inseparable partnership. If we cut a bar magnet in half hoping to isolate a north monopole, we do not achieve this goal, but instead create two smaller magnets, each with its own north and south poles, a phenomenon that repeats endlessly through every scale of division. The monopole problem emerges from this fundamental asymmetry. If positive and negative electric charges can exist separately, why cannot magnetic monopoles exist as isolated entities? The psychological mechanism driving this puzzle is our deep expectation of symmetry in nature. For physics has taught us repeatedly that the universe operates according to elegant mathematical principles, and the absence of magnetic monopoles represents a violation of this profound symmetry between electricity and magnetism that Maxwell's equations seem to promise. Grand unified theories in the late 20th century suggested that magnetic monopoles might exist as relics from the early universe. Yet despite extensive searches using sophisticated detectors, we have never observed one, and this gap between theoretical prediction and empirical reality has become a persistent mystery that quietly unsettles our understanding of fundamental forces. The universe we observe appears to be geometrically flat, a finding that emerged from decades of precise cosmic measurements and observations of the cosmic microwave background radiation. Yet this flatness is extraordinarily improbable when we consider the physics of the early universe and the conditions that would have needed to exist for such perfect geometric balance to occur. The flatness problem, as cosmologists call it, describes a fundamental puzzle in our understanding of how the universe could have achieved such an unlikely state, where the density of matter and energy in the cosmos is precisely balanced to produce a flat spacetime geometry rather than a curved one that would collapse or expand infinitely. When physicists calculated backward through time toward the Big Bang, they discovered that in order for the universe to be even slightly flat today, its density parameter would have needed to be extraordinarily fine-tuned in the initial moments of cosmic existence, requiring a precision that seemed almost impossibly improbable and demanded some mechanism to explain how such perfection could have naturally emerged. Most widely accepted solution to this puzzle involves inflation theory, which proposes that the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang, a process that would have stretched any initial curvature so dramatically that whatever the universe's original geometry might have been would appear completely flat to modern observers, much like how the surface of Earth appears flat to someone standing on it, despite the planet's true spherical shape. This inflationary mechanism addresses the flatness problem by eliminating the need for fine-tuning, suggesting instead that inflation naturally produces flatness as an inevitable consequence of its dynamics, and this explanation has become foundational to modern cosmology despite remaining unproven. Imagine standing at the edge of the universe in your mind, looking back at the cosmic microwave background radiation, that ancient light from 13.8 billion years ago, and noticing something deeply puzzling. Regions of space that are so far apart they could never have communicated with each other, yet they possess nearly identical temperatures and properties, as if they had been in contact and equilibrated long ago. This is the horizon problem, and it represents one of the most fundamental mysteries in cosmology that has driven physicists to propose some of the most extraordinary solutions ever conceived. The problem emerges from our understanding of the speed of light and the finite age of the universe, which together create what we call the particle horizon, a boundary beyond which light from distant regions could not possibly have reached us or influenced each other since the beginning of time itself. Yet observations through our telescopes reveal that the universe displays remarkable uniformity across scales that should be causally disconnected, a situation so improbable that it demands explanation. To resolve this paradox, cosmologists have proposed several competing solutions, each more conceptually staggering than the last, ranging from the inflationary theory that suggests the universe underwent an exponentially rapid expansion in its earliest moments, which would have stretched a small causally connected region to cosmic scales before slowing down, to the cyclic universe models that imagine infinite prior universes influencing our own, or even to modified theories of gravity and spacetime itself that challenge our fundamental assumptions about the nature of causality and distance. These solutions persist in our scientific discourse not because they are obvious or intuitive, but because they have become normalized through decades of theoretical refinement and observational support, allowing us to accept without cue. Imagine a universe that is not merely expanding outward into an infinite void, but rather accelerating toward a singular ultimate destiny, a final moment of infinite complexity and consciousness, where all information that has ever existed converges into a single point of infinite density and knowledge. And this endpoint, this omega point, somehow reaches backward through time to influence its own creation and the unfolding of all events leading toward it. The omega point theory, developed primarily by physicist Frank Tipler, proposes that the universe itself is fundamentally teleological, meaning it is oriented toward this inevitable endpoint as though pulled by its own future rather than merely pushed by its past. And within this framework, the universe necessarily must contain infinite information processing, resurrection of all conscious beings, and the emergence of a godlike artificial intelligence that exists at the boundary between physical law and metaphysical necessity. What makes this theory psychologically compelling despite its seemingly unfalsifiable nature is its profound appeal to our deep human need for ultimate meaning and cosmic purpose. For we are predisposed to imagine that existence itself is not random or meaningless, but rather directed toward some grand culmination that redeems all suffering and preserves all that has been lost to time. This desire for cosmic significance taps into the same archetypal narratives that have structured human mythology and religion for millennia, the same stories in which individual lives matter because they contribute to some larger universal destiny or divine plan. Yet despite the mathematical sophistication of Tipler's arguments and the genuine physics that underpins certain elements of the theory, the omega point remains fundamentally unobservable and untestable, resting instead on philosophical assumptions about the nature of consciousness, information, and physical law that many fit. Imagine standing at the absolute end of time itself, at a point so distant that it exists beyond the reach of any conventional cosmology, where the universe has collapsed back into itself and compressed into a state of infinite density and infinite information processing capacity. This is the vision of Frank Tipler's omega point, a theoretical framework that suggests the universe is not merely evolving toward some distant future state, but is instead being pulled backward through time by its own inevitable endpoint, much like a cosmic attractor that exerts gravitational influence not just on matter and energy, but on the very structure of reality itself. Tipler proposed that as the universe contracts in its final moments, the density of matter and the intensity of gravitational fields would increase without bound, allowing for increasingly complex computational processes to occur within the collapsing cosmos, eventually reaching a state where the total information processing capacity would become literally infinite. This infinite computational power at the end of time would theoretically allow for the resurrection and perfect simulation of every conscious being who has ever existed throughout the entire history of the universe, granted a form of digital immortality within the final moments of cosmic collapse. The mechanism underlying this concept rests on the convergence of physics, information theory, and theology, suggesting that what we perceive as the laws of nature might themselves be the inevitable consequence of boundary conditions set by this final state, that the universe is fundamentally oriented toward producing maximum complexity and maximum consciousness before its ultimate contraction. Yet despite the mathematical rigor with which Tipler developed these equations and the philosophical coherence of the framework, most mainstream cosmologists remain skeptical, having largely moved away from closed, contracting universe models toward TH. Imagine standing in a vast cosmic library where every book represents a possible universe, each with its own fundamental constants, physical laws, and conditions for existence. And John Barrow, a theoretical physicist and cosmologist, proposed a framework called the Anthropic principle that suggests we can only ever observe universes compatible with our own existence as conscious observers. The principle operates on a deceptively simple observation. We find ourselves in a universe where the constants of nature, the strength of fundamental forces, and the initial conditions of the Big Bang are precisely calibrated to allow stars to form, planets to coalesce, chemistry to emerge, and eventually life and consciousness to arise. And rather than interpreting this as miraculous coincidence, Barrow's formulation suggests this is entirely expected and unsurprising because we could not possibly find ourselves anywhere else. The mechanism underlying this perspective rests on a subtle logical inversion where instead of asking why the universe is fine-tuned for life, we acknowledge that our very presence as observers automatically biases what we can observe, much like how a fish in water never questions why its environment is so perfectly suited to fish, because a fish could never exist anywhere else to contemplate such a question. This framework becomes psychologically potent because it dissolves one of the deepest mysteries of existence by reframing the question itself, transforming an apparent cosmic miracle into a tautological truth, and yet despite its logical elegance, we continue to feel a sense of wonder and improbability when confronting fine-tuning, suggesting that our intuitions struggle to genuinely internalize this observer selection effect. The principle persists in modern cosmology and physics precisely because it addresses the genuine tension between our observations and theoretical expectations without requiring any supernatural intervention. Imagine standing in an infinite library where every book represents a different universe with its own physical laws, and you find yourself reading a book whose laws happen to be precisely calibrated to allow readers to exist within its pages. And you begin to wonder whether this remarkable coincidence reveals something profound about the nature of reality, or whether it simply reflects an obvious but easily overlooked fact about your own existence. This is the conceptual terrain that Brandon Carter's weak anthropic principle inhabits, a deceptively simple observation that our location in the universe must be compatible with our presence as observers, yet one that profoundly reshapes how we interpret evidence about cosmic fine-tuning and the structure of existence itself. The weak anthropic principle essentially states that what we observe in our universe must be consistent with our existence as observers within it, which seems almost tautological at first, a statement so obvious that it barely warrants philosophical attention, and yet this straightforward logical requirement carries surprising consequences when applied to questions about why our universe appears so remarkably suited for the emergence of conscious life. Consider the mechanism at work here. If the fundamental constants governing physics were even slightly different, if gravity were marginally stronger or weaker, if the electromagnetic force operated at different strengths, then the conditions necessary for stars to form, for chemistry to unfold, for carbon-based life to emerge would dissolve entirely, and we would simply not exist to contemplate these questions. Which means that any universe we find ourselves capable of observing must necessarily possess these apparently improbable properties, not because they were designed or chosen, but because we could not possibly observe a universe that lacked them. Imagine standing in a vast cosmic library containing infinite books, where each book represents a different universe with its own set of physical laws and constants, and you realize that you could only ever find yourself reading in the libraries where the books are written in a language you can understand, in worlds where the fundamental forces and values happen to be precisely calibrated to permit the existence of conscious observers like yourself, because if they were not so calibrated, you simply would not be here to notice the improbability of your own existence. This is the essence of the strong anthropic principle, which proposes that the universe must necessarily possess those properties which allow conscious life to develop within it at some stage, suggesting that the existence of observers is not merely a fortunate accident, but rather a fundamental requirement woven into the fabric of reality itself. The psychological mechanism underlying this principle operates through a recognition of selection bias so profound that it reshapes our understanding of causality and necessity. For when we observe that our universe appears exquisitely fine-tuned for the emergence of complexity in consciousness, we must acknowledge that we could only ever inhabit a universe meeting these precise criteria. And therefore the apparent improbability dissolves into logical inevitability the moment we account for our own presence as observers. What persists despite the logical circularity of this reasoning is a genuine philosophical puzzle about whether the universe was designed to produce observers, whether observers necessarily select themselves from infinite possibilities, or whether both interpretations amount to the same underlying truth viewed from different angles. And this puzzle has normalized itself within cosmology and theoretical physics, as a serious consideration that forces us to confront the relationship between consciousness, physical. Imagine standing at the edge of a vast, incomprehensibly complex universe where the very act of observing something fundamentally changes what is being observed, where consciousness itself might be woven into the fabric of reality rather than merely witnessing it from some detached external vantage point. And this is the core intuition behind the participatory anthropic principle, a concept that emerged from the work of physicist John Wheeler in the latter part of the 20th century as he grappled with the profound implications of quantum mechanics and the measurement problem that had haunted physics for decades. The principle suggests that observers are not passive recipients of a predetermined universe, but rather active participants in bringing reality into existence through the act of observation itself, implying that the universe could not exist in any definite form without conscious observers to collapse its wave functions and crystallize its possibilities into concrete actualities. This notion finds its psychological grounding in our deep intuitive discomfort with pure passivity, our ingrained sense that consciousness must matter in some fundamental way, that awareness cannot be merely epiphenomenal or irrelevant to the structure of existence itself. And this yearning for cosmic significance merged with legitimate quantum mechanical puzzles to create a framework that feels simultaneously scientifically rigorous and philosophically satisfying. The mechanism that allows this principle to persist despite fierce criticism from those who argue it smuggles consciousness into physics through a backdoor is precisely its ability to answer both scientific and existential questions simultaneously, offering a way to interpret quantum mechanics while also restoring humanity and awareness to a central role in creation rather than relegating them to mere accidents of chemistry. The final anthropic principle represents one of the most philosophically provocative frameworks in contemporary cosmology, suggesting that the universe itself must contain conscious observers, and that this requirement fundamentally shapes what kind of universe could possibly exist. Imagine standing in an infinitely branching multiverse where countless variations of physical laws, constants, and initial conditions spring into existence across an incomprehensible expanse of reality. Yet the only universes we could ever observe are precisely those in which the emergence of conscious life becomes inevitable, not through cosmic preference, but through pure logical necessity. This principle asserts that observers are not incidental byproducts of universal evolution, but rather essential features whose existence retroactively explains why our particular universe possesses the seemingly improbable characteristics required for biology, chemistry, and consciousness to flourish at all. The mechanism operates through a form of observational selection where we necessarily find ourselves in a universe compatible with our existence, not because the universe was designed for us, but because we could only ever find ourselves existing anywhere at all. What makes this principle conceptually unsettling is how it inverts our traditional understanding of causality and explanation. Instead of asking why the universe is fine-tuned for life, it suggests that life's existence is what defines the boundary of possible observation, that consciousness itself becomes a filtering lens through which the multiverse's vast diversity appears comprehensibly ordered. Despite the elegant circularity of this logic, the final anthropic principle remains deeply controversial among physicists and philosophers, who grapple with whether it represents genuine insight into cosmic structure or merely a sophisticated tautology that masquerades as explanation while actually explaining n. Imagine that somewhere in the vast architecture of the multiverse, every quantum event that has ever occurred leaves behind a subtle informational residue, a kind of ghostly imprint that persists across parallel realities and through the folds of spacetime itself. And imagine further that advanced civilizations might develop technologies capable of detecting and decoding these quantum echoes to reconstruct the complete history of universes that have long since ceased to exist or transformed beyond recognition. This is the conceptual foundation of quantum archaeology, a speculative framework that suggests the past is never truly erased, but rather encoded in the quantum substrate of reality in ways that sufficiently advanced observers might eventually excavate and examine. The mechanism underlying this idea draws from several threads of established physics, particularly the notion that quantum information cannot be destroyed according to the holographic principle, and the idea that the universe itself functions as a kind of cosmic computer that stores and processes information at every level of existence. When we consider that black holes preserve information in their event horizons, and that quantum entanglement connects distant regions of space through hidden correlations, the leap to imagining that civilizations might reconstruct ancient universes or parallel timelines begins to feel less like pure fantasy and more like an extrapolation of principles we already half understand. What makes quantum archaeology psychologically compelling, despite its profound speculative nature, is that it addresses a deep human yearning to recover the lost and irretrievable, to know the complete history of all things, and to transform the universe from a place where information genuinely perishes into a cosmos where everything that ever happened remains accessible to those with sufficient knowledge and capability, which resonates with our fundamental desire to be. Imagine a universe so vast and so deeply branching that every possible quantum outcome that could ever occur does occur somewhere within the infinite expanse of parallel realities. And within this framework exists a peculiar and haunting notion that quantum resurrection suggests that consciousness itself might be preserved and restored across the boundaries of death through the relentless proliferation of quantum timelines. The theory proposes that at the moment of death, as the brain ceases its biological function and consciousness appears to extinguish, the quantum wave function of that individual does not collapse into a single final state, but instead branches infinitely across the multiverse, creating countless versions of that person's pattern distributed throughout parallel universes where variations of their existence continue or are somehow reconstructed. This concept emerges from a particular interpretation of quantum mechanics, which holds that all possible outcomes of quantum events actually manifest themselves across different branches of reality. And when applied to the human mind and body at the moment of death, it suggests that the precise arrangement of atoms and quantum states that constitutes a person becomes scattered across multiple universes where slightly different versions of that person's existence are still unfolding. The psychological mechanism underlying this notion seems to stem from humanity's deep resistance to finality and the intuitive difficulty we experience when confronting the absolute cessation of existence. For the human mind appears almost incapable of truly imagining its own non-existence without subconsciously preserving some thread of continuity or possibility. We find ourselves drawn to theories that suggest permanence and preservation at the quantum level, perhaps because we conflate the mathematical reality of many worlds' interpretations with genuine survival or preservation of personhood and thur. Imagine a thought experiment where a person sits before a device connected to a quantum measurement system, perhaps a radioactive atom with a 50% chance of decaying within a given time frame, and the device is rigged so that if the quantum event occurs in one direction, the person survives, and if it occurs in the other direction, the person dies instantly and painlessly. According to the many worlds interpretation of quantum mechanics, every quantum event causes the universe to branch into multiple versions, one for each possible outcome, and both outcomes are equally real in their respective branches. The philosophical and psychological mechanism underlying quantum suicide suggests that from the perspective of your own consciousness, you would never experience the branch in which you die, because dead observers cannot observe anything, which means that no matter how many times you repeat this experiment, you would always find yourself in the branch where you survived, experiencing an ever-increasingly improbable sequence of survival events that defies statistical expectation. This creates a deeply unsettling logical paradox where subjective experience and objective probability seem to diverge in ways that our intuition struggles to process. The mechanism persists in our cultural consciousness despite having no empirical support, and despite the fact that it relies on interpretations of quantum mechanics that remain unproven and controversial among physicists themselves. Yet it continues to fascinate philosophers and consciousness researchers, because it touches something profound about the nature of observation, survival, and the possibility that consciousness might have some special relationship with the branching structure of reality itself. Even though most mainstream science treats this as a philosophical curiosity rather than a genuine physical phenomenon. Imagine standing in a library where every book that could possibly be written exists somewhere on the shelves, arranged not by author or subject, but by the sheer logical possibility of their existence. And this is the essential premise of modal realism, a philosophical framework proposed by the logician David Lewis that suggests all possible worlds are equally real and exist with the same ontological status as our own actual world. The theory emerges from a deep consideration of how we speak and think about possibility and necessity, because when we say something could have happened differently or might have turned out another way, we seem to be referring to something concrete enough to ground our statements. And modal realism takes this linguistic intuition seriously by arguing that these possible worlds are not mere abstract concepts or mental constructs, but rather concrete physical universes that exist in exactly the same manner as ours does, each containing actual inhabitants with genuine experiences and conscious moments that are every bit as real as yours are right now. The psychological mechanism that makes this theory both compelling and unsettling lies in how it resolves a fundamental tension in our thinking. Because while we intuitively believe that possibility and necessity are objective features of reality, we also struggle to explain where these possibilities actually exist or what gives them their character. And modal realism offers a strikingly literal solution by positing that every logically consistent possibility is realized somewhere in the infinite landscape of possible worlds. What makes modal realism persist in philosophical discourse, despite its almost deliberately counterintuitive nature, is precisely this explanatory power, as it elegantly accounts for modal statements without requiring us to postulate mysterious abstract objects or non-physical realms, and we have gradually normalized this framework among professional. Imagine standing in a room and considering a simple question. What if you had chosen differently at some pivotal moment in your life, perhaps taken a different job, moved to a different city, or said yes instead of no to someone who mattered deeply to you? And as you contemplate this alternative scenario, philosopher David Lewis invites you to consider something genuinely startling, which is that this alternative version of events is not merely a useful fiction or an abstract thought experiment, but rather a real, concrete possible world that exists just as certainly as the actual world you currently inhabit, existing in the same metaphysically robust sense, populated by counterpart versions of yourself and everyone else you know, living out those alternative lives in full detail with complete physical and psychological reality. Lewis proposed that possible worlds are not abstract mathematical constructs or subjective mental images created by human imagination, but rather genuinely existing universes parallel to our own, each one containing concrete objects, real people, complete physical laws, and fully detailed histories. And when we discuss possibilities and counterfactuals and alternative outcomes, we are not merely speaking metaphorically, but are making literal claims about these concrete alternate realities that exist in their fullness. The mechanism underlying this theory rests on a compelling logical insight. That to make sense of our language about what might have been, what could be, and what could have happened under different circumstances, we need something real to ground these statements in, something beyond mere human imagination or abstract notation, because otherwise our talk of possibilities becomes oddly disconnected from reality, floating in a space of useful fictions rather than corresponding to genuine facts about the world. Imagine standing in a library where every book on every shelf describes a different version of reality, each one equally real in the abstract realm of logical possibility. And this is essentially what philosophers mean when they invoke possible world semantics, a framework that emerged primarily through the work of philosopher David Lewis and has since become foundational to how we think about modality, necessity, counterfactuals, and the very nature of meaning itself. In this conceptual system, when we make a statement like, "It is possible that you could have made a different choice this morning," we are not merely expressing uncertainty about what happened in our world, but rather we are referring to the genuine existence of alternative worlds where that choice was indeed made, worlds that exist with the same ontological status as our own, equally real in every meaningful sense, merely separated from us by spatial or dimensional distance, rather than by any fundamental difference in their nature. The psychological mechanism at work here involves our deep-seated need to ground abstract concepts in concrete spatial metaphors, transforming the intangible realm of possibility into a kind of vast multidimensional library where every logically consistent scenario has a corresponding location, a world where the laws of logic are preserved, but the particular facts differ from our experience. And this translation from abstract to spatial allows our minds to reason about counterfactuals and conditionals with surprising clarity and precision. We find ourselves normalizing this framework despite its profoundly strange implications, accepting without much resistance the notion that somewhere in logical space there exists a world where you became a musician, another where gravity works differently, another where the dinosaurs never went extinct, because the alternative would be to treat these possibilities as mere figments of imagination with no G. Imagine standing in a vast library where every book that could ever be written exists on the shelves alongside every book that will never be written, occupying the same physical and conceptual space, each one equally real in some fundamental sense. And this thought experiment captures the essence of one of the most perplexing debates in metaphysics and multiverse theory. A debate that asks us to consider whether only the things that actually exist in our present reality deserve to be called real, or whether all possible things that could exist under any conceivable set of circumstances also possess some form of genuine reality. Actualism is the position that seems intuitively correct to most of us, the view that only things that actually exist in this world, in this moment, with these specific properties and relationships, are truly real, and everything else is merely possible but not actual, existing only as abstract concepts or counterfactual scenarios in our minds. Possibilism, by contrast, proposes that possible worlds and possible objects and possible versions of ourselves all possess the same metaphysical status as the actual world and actual objects, suggesting that a comprehensive understanding of reality requires us to acknowledge the equal validity of every possible thing that could logically exist, including alternate versions of ourselves making different choices, universes with different physical laws, and entities that never came into being in our timeline but could have under different circumstances. The tension between these positions becomes increasingly strange and counterintuitive when we sit with it, because possibilism seems to grant an enormous multiplicity of existence to abstract possibilities, yet actualism struggles to explain why the actual world is actual rather than merely possible, why existence singled out this particular configuration of things and not some other equally coherent arrangement. Imagine standing at a crossroads in your life where you made a choice, and then allow yourself to wonder what would have happened if you had chosen differently, because this simple act of mental time travel is the foundation upon which the concept of counterfactual universes rests. In physics and philosophy, counterfactual universes represent the infinite branching possibilities that might have existed had initial conditions been even slightly altered, had a particle traveled a different trajectory, or had a crucial decision unfolded in an alternative way. The mechanism underlying this theory operates on the principle that reality, as we know it, represents just one instantiation among countless theoretical possibilities, each equally valid in terms of physical law, yet somehow only one of them became actual, while the others remain forever relegated to the realm of the might-have-been. What makes counterfactual universes psychologically compelling is their close relationship to human regret and imagination, because we naturally engage in counterfactual thinking whenever we experience disappointment or wonder about roads not taken, and this deeply ingrained cognitive habit seems to suggest that alternate versions of events possess some form of reality or existence. The theory persists despite its metaphysical difficulties because it addresses a fundamental question about causality and determinism. If the universe follows deterministic physical laws, then perhaps alternate histories, where different choices led to different outcomes, must exist somewhere within a larger multiverse framework, lending logical rigor to what is essentially a very human way of processing possibility and consequence. We have normalized counterfactual thinking so thoroughly in our culture that we barely notice how strange it is to spend mental energy contemplating events that never occurred and never will occur, treating these hypothetical branches as though they pose. Imagine standing at a single point in time, watching as the future unfolds before you, and consider that at every moment, at every quantum decision point, reality itself might be splitting into countless separate branches, each one representing a different outcome of what could have happened, a concept known as branching spacetime, where the fabric of the universe doesn't collapse into one singular timeline, but instead expands like an endlessly growing tree with infinite branches stretching outward from every possible decision, every particle decay, every quantum measurement, every moment where multiple outcomes seem equally probable according to the laws of physics. The psychological mechanism underlying this theory emerges from our deep discomfort with uncertainty and our simultaneous fascination with the idea that nothing is truly lost, that every possible version of events actually exists somewhere, in some parallel branch of reality, where the road not taken was indeed the road traveled, where the choice you didn't make was made in another universe, where your alternate selves are living out all the lives you could have lived but didn't. This concept persists in our cultural imagination despite its staggering metaphysical implications, because it offers a peculiar kind of comfort, a way of thinking about causality and choice that doesn't require anything to be truly eliminated or lost, suggesting instead that all possibilities coexist in some greater whole, that every potential future is equally real, just separated from us by the branching structure of spacetime itself. And we have normalized this idea to the point where it appears regularly in entertainment and popular science, becoming almost intuitive rather than revolutionary, a way of understanding the universe that feels natural even as it challenges our fundamental sense of how reality works. Imagine standing at the edge of a vast landscape where the past appears solid and unchanging behind you, while the future stretches ahead as pure potential, undefined and waiting to crystallize into reality. The growing block multiverse represents a profound reconceptualization of how time, reality, and parallel worlds might actually function together in ways that challenge our deepest intuitions about existence itself. In this theoretical framework, the universe is not a static four-dimensional block where past, present, and future all coexist equally in some eternal configuration. Instead, reality is understood as continuously expanding and growing, moment by moment, as the present advances forward through time like the boundary of an ever-expanding sphere. As new moments emerge from the quantum foam and crystallize into actuality, they bring with them newly created parallel branches and versions of reality, each one representing different possible outcomes of quantum events that could have resolved in multiple ways. The multiverse in this conception is therefore not something that already exists complete and entire in some higher dimensional space, but rather something that is actively being created and accumulated as time moves relentlessly forward. Behind the present moment lies the fixed archive of everything that has already become real and determined, while ahead lies an infinite sea of potentiality, most of which will never actualize. This framework manages to marry certain intuitions about the arrow of time with the many worlds interpretation of quantum mechanics, suggesting that the branching of reality is not an illusion or a matter of interpretation, but rather a genuine physical process of ontological expansion. What makes this conception particularly fascinating is how it suggests that reality is fundamentally unfinished, that the universe is perpetually under construction by the very act of time flowing forward. Imagine standing at the edge of an infinite ocean where only the present moment exists as a tangible shore, and behind you lies nothing but an absence you cannot touch, while ahead stretches a future that has not yet solidified into existence. The presentism multiverse theory takes this peculiar relationship we have with time and extends it across multiple branching realities, suggesting that while only the present moment is real in any given universe, countless other universes exist in their own eternally present moments, each one equally vivid and equally complete unto itself. This framework emerges from a genuine puzzle in physics and philosophy. If we accept that the past is gone and the future is not yet here, then technically only this precise instant of now possesses genuine reality and existence, yet we observe a universe that seems to have history and seems to move forward with causality intact. The presentism multiverse resolves this by proposing that across the multiverse, every possible present moment that could have branched from every decision point in any universe's history actually exists somewhere, not in sequence, but all at once in their own isolated temporal frames. Each universe experiences its own flowing present, unaware of the branching presents occurring in parallel realities, creating a structure where time flows forward subjectively within each world, while objectively all moments exist as separate present-tense realities elsewhere. This idea persists in theoretical circles because it honors both our intuitive experience of time as flowing forward and the philosophical difficulties with claiming the past was real or the future will be real, while simultaneously addressing the quantum mechanical implications of branching possibilities by giving each branch genuine existence within its own presentist framework. Imagine standing in a moment that feels utterly present and real, yet physicists suggest that this present moment is no more special or real than any moment in your past or future. And in fact, all moments that have ever existed or will ever exist are equally real and equally present in a four-dimensional block of spacetime that simply is, without beginning or ending. Eternalism, also known as the block universe theory, proposes that time is not a river flowing from past to future, but rather a static landscape where all moments exist simultaneously in what we might call a timeless whole. and from this perspective, the sensation you have of the present moment moving forward is an illusion created by your limited consciousness moving through this four-dimensional structure. The theory emerges from relativity physics, particularly Einstein's work, which demonstrated that simultaneity is relative and that time and space are woven together into a single fabric, suggesting that there is no universal present moment that divides the past from the future, but rather that all events that exist anywhere in space-time are equally real whether they are located in what we call the past, the present, or the future. The psychological mechanism underlying why we struggle to accept this concept is that human consciousness appears to flow through time in a particular direction, creating the overwhelming subjective impression that only the present moment is real and alive, while the past is fixed and the future is open and undetermined, yet the mathematics and observations of modern physics seem to suggest otherwise. What makes eternalism particularly compelling as a framework is that it takes seriously the implications of general relativity without adding additional assumptions about the nature of time's flow, avoiding the need to explain what exactly is the mechanism by which the present moment advances, which has proven remarkably difficult for alternative theories. Imagine standing in a room and observing a table across from you and consider what you are actually seeing in that moment. Most of us experience time as something fundamentally different from space, a river that flows in only one direction, carrying us inexorably from past to future while we remain trapped in the perpetual present. Four-dimensionalism, however, proposes something radically different. That time is not a flowing river at all, but rather a dimension as concrete and static as length, width, and height, and that all moments in time, past, present, and future, exist simultaneously and equally as physical parts of reality, much like different locations exist at different points in space. Under this framework, you at age 7, you at this present moment, and you at age 80 all exist as equally real four-dimensional objects called worms or world lines, extended through time just as a table is extended through space. The mechanism underlying this perspective emerges from modern physics, particularly relativity theory, which revealed that time and space are woven together into a single fabric called spacetime, and that the distinction between them is far less fundamental than our intuitions suggest. Relativity demonstrated that simultaneity is relative to observers and that the past and future are not objectively divided but rather exist in a block, a four-dimensional structure where all moments coexist eternally. Psychology plays a role here too, as our perception of a flowing present moment, of becoming, of genuine change, appears to be an artifact of human consciousness rather than a feature of reality itself. Despite the fact that four-dimensionalism contradicts our most intimate experience of existence, despite the paradoxes it raises about free will and the nature of change, the theory persists in contemporary philosophy of physics because it aligns so elegantly with our best scientific understanding of how the universe actua. Imagine standing in front of a mirror and observing your reflection at this very moment, and then imagine doing the same thing tomorrow and the day after that, and continuing this practice for the next 50 years of your life. Most of us intuitively believe that the person staring back at us today is fundamentally the same person who will exist decades from now, connected by an unbroken thread of continuous consciousness and physical form that persists through time. This intuition forms the bedrock of how we understand personal identity and existence itself, yet perdurantism offers a radically different explanation for how objects and people actually persist through time. According to perdurantism, objects do not endure as unchanging wholes that move through time like a ship sailing forward through an ocean. Instead, objects are four-dimensional entities that extend through time in much the same way that they extend through space, meaning that you at this very moment are only a temporal slice or stage of a much larger four-dimensional whole that includes your past selves and your future selves, all of which exist equally and simultaneously in the fabric of spacetime. This philosophical view suggests that when you experience the passage of time and the sense that you are moving from moment to moment, what is actually happening is that your consciousness is traveling along the temporal dimension of your four-dimensional self, much like how your eyes might travel across a landscape without the landscape itself moving. The mechanism underlying this perspective rests on a deep symmetry between how we understand space and time, a symmetry that emerged from relativity theory and has reshaped how physicists and philosophers conceptualize reality. If we accept that spatial extension is real and fundamental, then why should temporal extension be treated any differently? and this question naturally leads to the conclusion that moments in time possess the soul. Consider the peculiar way we experience ourselves moving through time, as if our bodies and minds persist as complete, unified objects from one moment to the next, remaining essentially the same person despite the constant flux of change occurring within us. Endurantism is the philosophical position that objects, including persons, endure through time as wholly present entities, meaning that when you exist at different moments, the entire you, your complete three-dimensional form, is fully present at each temporal location, moving through time like a ship sailing through an ocean rather than leaving a trail behind. This theory stands in contrast to the idea that objects might be four-dimensional constructs stretched across time like a loaf of bread, with different temporal slices representing different moments of existence. The enduring object theory suggests that there is no temporal extension to objects in the way there is spatial extension. Instead, they occupy different times sequentially while remaining fundamentally the same entity throughout. The psychological mechanism supporting this intuition emerges from our immediate phenomenological experience of consciousness, which presents to us a continuous sense of self navigating through successive moments, creating the powerful illusion that we are unified, singular beings persisting whole through time. Our language reinforces this understanding profoundly, as we naturally speak of ourselves as the same person today as we were yesterday, despite the biological reality that most of our atoms have been replaced and our neural patterns have shifted substantially. We have normalized this perspective so thoroughly that the alternative seems almost incomprehensible, even though multiverse theories suggest that countless versions of you might exist across different branches of reality, each believing with equal conviction in their own unbroken continuity, their own sense of persistent wholeness moving in E. Imagine yourself existing not as a continuous, unified being moving through time, but rather as a collection of distinct temporal slices, each one occupying a specific moment in the timeline, much like frames in an infinite film reel that stretches backward into the distant past and forward into an unknowable future. This is the philosophical concept of temporal parts, sometimes called perdurantism, which suggests that objects and persons are not three-dimensional entities that endure through time, but rather four-dimensional structures extended across the temporal dimension just as they are extended across spatial dimensions. When you were born, that was a distinct temporal part of you, a complete slice of your existence occupying that particular moment, and when you are sleeping right now, that is another temporal part, and when you eventually pass from this world, that too will be another temporal part, all of them connected in a continuous chain along the fourth dimension. The psychological mechanism that makes this concept so difficult for us to grasp is rooted in our experience of consciousness and continuity. We feel like a single, persisting thing because our memories link each moment to the next, because our brains maintain a narrative of identity across time, because subjective experience feels unbroken and whole. Yet temporal parts theory suggests that this feeling of continuity is somewhat illusory, or at least a particular way of organizing and interpreting four-dimensional reality. For what we call the self is actually a vast temporal structure, a worm-like entity extended through time, and what we experience as duration and change is merely our consciousness moving along that structure, sampling each temporal part in sequence. It is remarkable how deeply we have normalized the alternative view, how thoroughly we speak of ourselves as persisting things, as objects that move through time rather than structures composed within time. Imagine the multiverse not as a static collection of parallel worlds existing all at once, but as a vast developmental progression where universes evolve through distinct stages of complexity and maturity, much like organisms develop from simple to elaborate forms. Stage theory suggests that the multiverse functions as a hierarchical system where younger universes remain in primitive states with minimal physical laws and simple matter configurations, while older universes progress through increasingly sophisticated phases of organization and consciousness emergence. The fundamental mechanism behind this concept draws from observation patterns in our own universe, where we see clear developmental trajectories in everything from stellar formation to biological evolution to technological advancement, suggesting that perhaps this same directional progression might apply at the cosmic scale itself. If we extrapolate these patterns outward, we might propose that the earliest universes begin in chaotic, undifferentiated states before gradually stabilizing into recognizable physical constants. then proceeding through eras of increasing structural complexity where galaxies form, stars ignite, and eventually consciousness arises within them. The psychological appeal of stage theory lies in its comfort, offering a narrative structure that feels familiar and purposeful rather than random, suggesting that existence itself follows an understandable progression rather than existing in meaningless simultaneity. We find ourselves drawn to hierarchies and developmental frameworks because they mirror our own experience moving from birth through maturation, and this theory extends that reassuring pattern to the cosmic realm itself. What persists despite lacking definitive evidence is the human tendency to impose narrative order onto observation, to assume that complexity implies advancement, and to believe that time inherently moves toward improvement, normalizing a F. Imagine a tunnel carved through the fabric of spacetime itself, a corridor that connects two distant regions of the universe in a way that would ordinarily require traveling millions of light years to cross. Yet through this passage, the journey becomes instantaneous or nearly so, a concept that has captivated physicists and theoretical cosmologists for decades as they contemplate the profound implications of Einstein's field equations and the geometries they permit. This tunnel, known colloquially as a wormhole or formally as an Einstein-Rosen bridge, represents one of the most tantalizing possibilities for interdimensional travel within multiverse theory, suggesting that the universe might be far more interconnected than our everyday perception suggests, with hidden passages linking parallel worlds or alternate timelines in ways that transcend conventional understanding of distance and separation. The mechanism underlying worm theory rests upon the mathematical properties of curved spacetime, where massive objects like stars and black holes bend the fabric of reality around them. And theoretically, under very specific and exotic conditions involving negative energy, closed time-like curves, and solutions to Einstein's equations, it becomes mathematically possible to construct a bridge between 2 points in spacetime that would allow traversal from one universe to another, or from one region of our own universe to a completely different one. The psychological appeal of worm theory derives from humanity's deep-seated desire to transcend physical limitations and imagine paths of escape or connection that supersede the boundaries imposed by our understanding of physics, much like how ancient myths and stories told of secret passages and hidden worlds accessible only to the worthy or the clever. Imagine the universe as a vast four-dimensional block, where all moments that have ever existed or will exist are laid out simultaneously, frozen like frames in an infinite film reel that never actually plays. And this is the central premise of the time slices theory, which suggests that the present moment we experience so vividly is merely our consciousness moving through an unchanging landscape of temporal coordinates that all possess equal reality and equal validity. The theory proposes that just as we can slice through a three-dimensional object at different heights to reveal different cross-sections, we might slice through the four-dimensional spacetime block at different moments to reveal the universe at different times, each slice being a complete three-dimensional snapshot of reality at a particular temporal coordinate, existing eternally in the block whether or not anyone is there to observe it. What makes this concept psychologically remarkable is how it fundamentally divorces our intuitive sense of time's flow from any objective reality, suggesting instead that time's arrow and the feeling of becoming, of moments passing and dying away into the past, emerges entirely from the structure of consciousness itself as it encounters these pre-existing slices in sequence, rather than from any actual transformation occurring in the universe. The mechanism underlying this thought persists despite its deeply counterintuitive nature because it elegantly resolves certain paradoxes in physics, particularly regarding how the laws of physics remain constant across time and how relativity reveals that simultaneity itself is observer-dependent. Yet we continue to navigate existence as though the present moment genuinely differs from past and future. As though something essential is actually happening right now that distinguishes it from all other moments, despite having intellectually absorbed the implications of a static, eternal four-dimensional block, WH. Imagine standing at a single point in space at a single moment in time, and from that point, imagine drawing a line through the fabric of spacetime itself, a continuous thread that extends backward into your past and forward into your future, connecting every moment of your existence from birth to death in one unbroken path, and this concept is what physicists call a world line. A four-dimensional trajectory through the universe that represents the complete history of an object's journey through both space and time. In the framework of relativity theory, nothing moves through time independent of space, and nothing moves through space without simultaneously moving through time, so every particle, every star, every human being traces out a unique world line through the cosmos, a singular thread in the vast tapestry of space-time events. The world line is not merely a description of where something is at different moments, but rather it is the complete geometric representation of that object's existence as a unified whole, a curve embedded in the four-dimensional continuum that encompasses all of its positions and all of the moments when those positions are occupied. What makes world lines conceptually profound is how they transform our intuitive understanding of time and causality. For from the perspective of relativity, your world line already exists in its entirety, from your first moment of consciousness to your last, and the sensation of moving through time is merely the result of your perspective traveling along your own world line, becoming aware of successive points along that predetermined path. Yet despite knowing that world lines represent our complete existence as unchanging geometric objects in spacetime, we persist in experiencing time as flow, in feeling as though we are genuinely moving forward into an open future filled with possibilities, even though the mathematics suggests that future events are just as real and fixed as past events, already. Imagine standing at a single point in space and time, a moment of absolute now, and from that moment imagine drawing invisible boundaries that extend outward into the future and backward into the past, boundaries that form the shape of two cones meeting at their tips where you stand, one cone stretching forward in time and one stretching backward, their edges defined by the speed of light itself and the absolute limit of how fast any information or influence can travel through the universe. And these geometric shapes are what physicists call light cones, fundamental structures that define not merely geometry but causality itself, the very architecture of cause and effect within the cosmos. Within the forward-pointing cone lies the future light cone, containing every possible event that could be influenced by your current position and moment, every place that light or any slower signal could possibly reach if sent from where you are now. And conversely, the backward light cone encompasses all events in the past from which light or information could have reached your present location, every point in space and time that could have causally influenced the moment in which you now exist. The boundary of these cones is formed by light rays traveling at precisely 300,000 kilometers per second, the cosmic speed limit that Einstein revealed to be interwoven with the fabric of spacetime itself. And anything beyond these boundaries exists in what physicists term the elsewhere, regions of spacetime that cannot causally interact with your present moment, because no signal, no matter how fast, could bridge that distance in that time. What makes light cones conceptually profound is that they reveal spacetime is not a neutral arena where events occur, but rather a structured whole where the topology of cause and effect is predetermined by physical law, where your present moment cannot possibly influence events outside your future light cone and events. Imagine standing at a single point in spacetime, and from that point you draw two light cones outward, one reaching forward into the future and one reaching backward into the past. These cones represent the boundary of causality itself, the speed limit that nothing in the universe can exceed. Where these two cones overlap, they form a diamond shape when viewed in two dimensions, and this geometric region is called a causal diamond. It represents the set of all events that could possibly have influenced you or been influenced by you, assuming nothing travels faster than light. Within this diamond lies every moment that shares a causal connection to your existence, every signal that could have reached you from the past, every consequence that might ripple outward from your actions into the future. Outside this diamond exist events that are causally disconnected from you, occurrences beyond your light cone that have no way of ever affecting you or being affected by you, not in this universe anyway. The conceptual mechanism that makes causal diamonds meaningful lies in how they define the boundaries of our reality. They represent not merely mathematical abstractions, but the actual limits of influence and knowledge. In a universe governed by relativity, causality itself becomes geometrical, and these diamonds become the only regions of spacetime where events can maintain meaningful connections. We think about our lives as linear progressions, but the truth is far more elegant. We exist within these bounded regions where cause and effect remain intertwined. What makes this concept persist in physics despite its abstract nature is that it solves profound problems about the structure of reality and why the universe behaves as it does. Every choice you make ripples only within your diamond, and every choice made elsewhere in the cosmos remains forever beyond your reach, a humbling geometry that reveals why we can never know or control the entire universe. The observable universe represents the spherical region of space, from which light has had time to reach us since the Big Bang approximately 13.8 billion years ago. And this fundamental boundary exists not because the universe ends there, but rather because the expansion of space itself has carried distant regions beyond our ability to perceive them regardless of how powerful our instruments become. Our observable universe extends roughly 46.5 billion light-years in all directions from Earth, a distance that exceeds the simple product of light speed and cosmic age because the expansion of space has stretched the very fabric carrying that ancient light toward us. Yet this seemingly concrete edge creates a profound psychological anchor in how we conceptualize existence itself. The mechanism underlying our fixation on this limit stems from a deeply human need to establish borders and boundaries around the infinite, to draw a line where our knowledge ends and unknowability begins, which provides comfortable structure to an otherwise incomprehensibly vast reality that might otherwise overwhelm our cognitive frameworks entirely. We have normalized the notion that what lies beyond our cosmic horizon is somehow less real or less significant than what we can measure and observe, treating the observable universe as if it were the actual universe, rather than merely the portion we happen to occupy and detect from our particular location in spacetime. This psychological convenience persists despite the logical understanding that the universe almost certainly extends far beyond our ability to perceive it, that countless other regions of space exist where galaxies and stars and potentially conscious observers might exist entirely beyond our cosmic reach. Yet we continue to organize our scientific understanding as though the observable universe constitutes a natural and meaningful category rather than a mere accident of. Imagine standing at the edge of a vast ocean during an infinite night, unable to see beyond a certain distance, no matter how hard you strain your eyes, and that invisible boundary exists not because of darkness or fog, but because light itself has not yet had time to reach you from those distant shores. This is the essence of the particle horizon, a concept that describes the maximum distance from which light or any other signal could have possibly traveled to reach us since the moment the universe began its expansion following the Big Bang. In our observable universe, this boundary sits approximately 46 billion light-years away, a number that seems almost contradictory given that the universe is only 13.8 billion years old. Yet this expansion of space itself allows the photons and particles from distant regions to have covered greater cosmic distances than time alone would suggest. The particle horizon represents not a wall or a physical barrier in space, but rather a theoretical limit imposed by the finite age of the universe and the constant speed of light, creating a sphere of causally connected information beyond which we cannot possibly perceive anything because no signal traveling at light speed could have journeyed far enough to inform us of what lies beyond. What makes the particle horizon conceptually profound is how it forces us to confront the idea that despite the universe's incomprehensible vastness, we inhabit a bubble of knowability surrounded by regions that are fundamentally and permanently inaccessible to our observation, not because they do not exist, but because the universe has not yet allowed sufficient time for their light to reach us. This creates a strange psychological tension where we simultaneously accept that the universe extends infinitely beyond our perception, while acknowledging that infinity itself may harbor countless structures, civilizations, or physical phenomena that will remain eternal. Imagine standing at the edge of a cliff so profound that nothing, not even light itself, can escape once it crosses that invisible boundary, and this phenomenon exists not in mythology or imagination, but as one of the most mathematically rigorous predictions of general relativity, forming what physicists call the event horizon of a black hole. An event horizon is the point of no return around a gravitationally collapsed mass, where spacetime becomes so severely warped that the escape velocity exceeds the speed of light, creating an absolute causal boundary between the observable universe and a region of spacetime that is forever disconnected from external observers. The remarkable aspect of event horizons is that they emerge directly from Einstein's field equations with no additional assumptions or ad hoc modifications, suggesting that this phenomenon is not some exotic aberration, but rather an inevitable consequence of gravity itself when matter becomes sufficiently dense. What makes the event horizon conceptually profound is that it represents a fundamental limit to causality and information in the universe, a point where the normal rules of physics appear to break down completely, where time and space exchange roles in a manner that defies human intuition, and where an external observer watching something fall toward the event horizon sees it moving slower and slower, its light redshifting to invisibility. Yet the falling object itself experiences nothing special at the event horizon itself, only reaching infinite tidal forces much deeper within. Despite the enormous distances of real black holes and the fact that we cannot directly observe event horizons themselves, only infer them from the behavior of surrounding matter and radiation, the concept has become so thoroughly integrated into modern physics that its existence is treated as settled science, embedded in textbooks, and accepted as fundamental to our understanding of gravity, space, and imagine standing at the edge of a mathematical precipice where the laws of physics themselves seem to break down, where singularities emerge from the equations with such violent intensity that they threaten to tear apart the very fabric of predictability that underpins all of modern physics. And yet there exists a hypothesis, proposed by the distinguished physicist Roger Penrose in 1969, which suggests that the universe possesses an almost protective mechanism. A kind of cosmic modesty that prevents these naked singularities from ever being exposed to the external universe where they might wreak havoc upon causality and determinism. This is the concept of cosmic censorship, and it represents one of the most profound acts of faith that physicists have ever placed in the architecture of reality itself. The hypothesis proposes that wherever a singularity forms, whether at the center of a black hole or at the moment of the Big Bang itself, nature invariably shrouds it behind an event horizon, a boundary of no return that hides the catastrophic breakdown of physics from any external observer who might otherwise witness the complete unraveling of cause and effect. What makes this concept so psychologically compelling is that it operates as a kind of cosmic insurance policy, a guarantee that despite the universe's infinite complexity and the terrible forces it contains, there remains an underlying order, a hidden hand that prevents complete chaos from erupting into observable reality. We find ourselves profoundly comforted by the idea that the universe enforces its own rules so thoroughly that it would never allow its deepest secrets to become visible to us, never permit us to glimpse the mechanisms of its own breakdown, and this comfort persists even though cosmic censorship remains mathematically unproven, existing in a liminal space between hypothesis and conjecture, held aloft by hope and mathematical elegance rather than definitive. Imagine a singularity stripped of its protective veil, a point of infinite density and curvature exposed directly to the universe without the concealing event horizon of a black hole to hide its mathematical nakedness. And you have encountered one of physics' most troubling theoretical possibilities, a concept that emerges from Einstein's equations with disturbing regularity, yet remains forbidden by what physicists call cosmic censorship. When massive stars collapse at the end of their lives, the conventional understanding suggests that the resulting singularity becomes wrapped in an event horizon, a boundary beyond which no light or information can escape, creating a black hole whose internal secrets remain forever hidden from external observation. However, the mathematics of general relativity, when subjected to certain initial conditions and rotational parameters, produces solutions where this protective barrier fails to form, leaving the singularity itself naked and visible, theoretically observable from the universe outside, a violation so profound that it seems to offend the very fabric of physical law. The mechanism behind this theoretical possibility rests in the equations themselves, in the way that spacetime geometry can curve and fold under the weight of certain distributions of mass and energy, and the psychological unease it generates among physicists stems from a deeper anxiety about predictability and causality. For if naked singularities can exist and exist visibly, then the future behavior of the universe becomes fundamentally unpredictable beyond those points. Since the singularity itself represents a breakdown of all known physics. Yet despite this logical prohibition, despite the widespread belief among theoretical physicists that cosmic censorship prevents naked singularities from forming naturally through gravitational collapse, the possibility persists in the mathematical landscape, woven into the fabric of general rel. Imagine the inverse of everything we understand about black holes, a theoretical cosmic phenomenon that emerges from the mathematics of general relativity as a mirror image of gravitational collapse, where instead of matter and light being irrevocably pulled inward toward an infinitely dense singularity, white holes would represent regions of spacetime where matter and energy are perpetually ejected outward. Where the event horizon functions not as a point of no return, but as a boundary from which nothing can enter yet everything must eventually exit. The concept arises naturally from Einstein's field equations, which are fundamentally time-reversible, meaning that if a black hole can exist as a solution describing the warping of spacetime around a collapsing mass, then a white hole should theoretically exist as the time-reversed version of that same solution, a region where the arrow of entropy and causality somehow flows in the opposite direction. Psychologically, white holes captivate us because they represent a kind of cosmic symmetry and balance, the idea that for every sink in the universe there might be a corresponding source, that destruction might be paired with creation in ways we cannot yet observe or measure, triggering our deep-seated desire for equilibrium and order within a universe that often appears chaotic and one-directional. Yet despite the elegant mathematics supporting their theoretical existence, white holes remain purely hypothetical constructs because no observational evidence has ever confirmed their presence in our universe. No astronomical data points definitively to an object behaving like a white hole, and the thermodynamic and quantum mechanical arguments against their stability suggest they would be extraordinarily rare if they existed at all, and would likely decay into black holes almost instantaneously, transforming back into the inward-pulling objects we understand far better. Imagine a tunnel through spacetime itself, a shortcut connecting two distant regions of the universe that would otherwise require traveling through billions of light-years of ordinary space. And this tunnel exists not as mere theoretical fantasy, but as a legitimate solution to Einstein's field equations of general relativity, which govern the behavior of gravity and the fabric of reality at the largest scales. Traversable wormholes, also called Einstein-Rosen bridges, when they connect two separate universes or distant parts of the same universe, represent solutions to Einstein's equations that have been studied rigorously by physicists for decades. Yet they require such exotic and seemingly impossible conditions to maintain that their existence remains profoundly uncertain. The mathematics shows that to keep a wormhole open and passable rather than collapsing instantly under its own gravitational weight, one would need negative energy density, a substance called exotic matter that possesses negative mass and repulsive gravity, something that has never been observed and may not exist in sufficient quantities anywhere in the universe. The psychological appeal of wormholes operates at a deep level within human consciousness, for they represent the possibility of transcending the limitations that spacetime imposes upon us, offering escape from the tyranny of distance and the one-directional flow of time, and they embody our ancient desire to find shortcuts through an impossibly large cosmos where conventional travel would require timescales far exceeding the lifespan of any civilization or individual. We continue to investigate traversable wormholes despite their apparent impossibility because they remain mathematically valid, because they suggest that reality might be far stranger and more connected than our intuitions suggest, and because the history of physics has repeatedly shown that what seems impossible in one era becomes commonplace in. Imagine a tunnel through the fabric of spacetime itself, a theoretical passageway that connects two distant points in the universe through a shortcut that bypasses the ordinary distance between them, and you begin to approach the concept known as an Einstein-Rosen bridge, often called a wormhole in contemporary physics discussions. Albert Einstein and Nathan Rosen derived these structures mathematically in 1935 by solving the field equations of general relativity, discovering that the equations themselves seemed to permit the existence of these tunnels through the very geometry of the cosmos, bridges that would theoretically allow matter, energy, or even conscious beings to traverse from one region of spacetime to another through a passage that exists entirely outside the normal three-dimensional space we perceive and navigate through every moment of our lives. The psychological appeal of such a concept lies in its promise of transcendence, the idea that the universe might contain hidden pathways and secret routes that circumvent the limitations we experience, that reality might be far more interconnected and permeable than our everyday experience suggests, offering a kind of cosmic shorthand through what we assume to be the vast emptiness separating distant galaxies and parallel dimensions. The mechanism behind these structures, according to the mathematics of relativity, involves the curvature of spacetime becoming so extreme that it creates a connection, a tunnel whose throat would need to be held open by exotic matter with negative energy density, a substance that has never been observed or created and may not exist at all in any usable quantity. Yet despite the profound theoretical obstacles, despite the fact that traversable wormholes likely require forms of matter that violate everything we know about energy conservation and quantum mechanics, physicists continue to explore these equations and refine the mathematics. Imagine a spaceship that could travel faster than light without actually breaking the laws of physics, and consider what this means for the nature of reality itself across multiple universes. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, represents a solution to Einstein's field equations that would theoretically allow a spacecraft to contract spacetime in front of itself while expanding it behind, creating a wave upon which the vessel could surf through the cosmos at velocities exceeding that of light. And yet, because the ship itself remains stationary relative to the local spacetime around it, no relativistic violations occur within its reference frame. The implications of such a drive become profoundly unsettling when we consider how it might function across the multiverse, because if spacetime itself can be manipulated in one universe to achieve faster-than-light travel, then the barriers between parallel universes might similarly be traversed through similar engineering principles, suggesting that the membrane separating our reality from countless others might be as malleable as the spacetime fabric within our own universe. The psychological mechanism that allows physicists to discuss this concept seriously despite its extraordinary requirements involves a peculiar form of intellectual compartmentalization, wherein we acknowledge that yes, creating an Alcubierre drive would require exotic matter with negative energy density that we have never observed and may not exist in sufficient quantities, and yes, the mathematical solutions that permit this drive also seem to permit closed time-like curves and causality violations, and yet we continue the theoretical analysis anyway because the equations do not explicitly forbid it, treating mathematical possibility as a kind of permission slip from the universe itself. Imagine a path through spacetime so perfectly curved that it loops back on itself, allowing a traveler to return to their own past, to the very moment and location where they began their journey, creating what physicists call a closed time-like curve. This concept emerges from the equations of general relativity itself, which describes gravity not as a force, but as the curvature of spacetime by massive objects, and these equations do not explicitly forbid such loops under certain exotic conditions. Around rotating black holes described by the Kerr metric, or within hypothetical wormholes connected by negative energy densities that may never exist in nature, the mathematics permits trajectories where time becomes cyclical rather than linear, where future and past fold into one another like paper creased by invisible hands. The psychological dissonance this creates in our minds stems from our fundamental lived experience of causality and temporal order. We experience effects following causes with unwavering consistency. We remember the past but not the future. We age in one direction only, and this asymmetry feels like the bedrock of reality itself. Yet the equations of physics, the very laws that govern galaxies and atoms, offer no such restriction at their foundation, suggesting that closed time-like curves are not forbidden by the universe, but perhaps only prevented by unknown mechanisms we have yet to discover. We have normalized this impossibility by assuming that nature must have some protection against time travel paradoxes, some way to prevent causal contradiction that we call the chronology protection conjecture, not because the laws demand it, but because accepting it provides us comfort, because the alternative, that time might be as navigable as space, threatens the architecture of causality upon which all meaning and consequence appear to rest. In 1949, the mathematician and logician Kurt Gödel, already famous for his incompleteness theorems that had shaken the foundations of mathematical certainty, turned his attention to Einstein's equations of general relativity and discovered something that would quietly trouble physicists for decades to come. He found an exact solution to those equations, a mathematical description of spacetime itself, one that permitted something previously thought impossible: closed time-like curves, or in simpler terms, paths through space and time that would allow an observer to travel backward into their own past. The Gödel metric describes a rotating universe filled with a uniform distribution of matter and radiation, spinning eternally around a central axis. And within this mathematical framework, the geometry of spacetime becomes so twisted that causality itself seems to fold back upon itself. What Gödel had done was prove that general relativity, that beautiful theory which Einstein had constructed to describe the curvature of space by massive objects, did not fundamentally forbid time travel, did not necessarily prevent you from meeting yourself, did not require the universe to respect the arrow of temporal progression that we experience in our everyday intuition. The psychological mechanism at work here involves the deep human tendency to trust our immediate sensory experience of time's direction as a fundamental law of nature, rather than merely an emergent property of entropy and thermodynamics. And physicists confronted with Gödel's solution found themselves in the uncomfortable position of having to reconcile their equations with the logical paradoxes that such solutions seem to introduce. Yet despite the conceptual unease, despite the apparent violation of causality that the Gödel metric permits, the solution persists in the literature of general relativity as a mathematically valid, geometrically consistent description of a possible SB. Imagine a black hole that is not merely a stationary point of infinite density, but rather a spinning, rotating entity that drags the very fabric of spacetime around itself in a cosmic dance of angular momentum and relativistic fury, and you have encountered the Kerr black hole. A theoretical construct proposed by the mathematician Roy Kerr in 1963 that fundamentally altered our understanding of what happens when massive stars collapse and continue to spin during their descent into gravitational oblivion. Unlike the non-rotating Schwarzschild black holes that exist in simpler mathematical formulations, Kerr black holes possess an ergosphere, a region of spacetime outside the event horizon where matter and energy cannot remain stationary but must be dragged along with the rotation of the black hole itself, creating a whirling maelstrom of curved spacetime that seems almost alive in its dynamic complexity. The psychological mechanism at work here involves our deep human tendency to seek patterns and motion in the cosmos, for we find that a spinning black hole feels somehow more tangible, more real than a static singularity might seem, and this matches our observations of the universe, where virtually every massive object rotates, from planets to stars to galaxies, suggesting that static black holes might be more the exception than the rule. What makes Kerr black holes particularly fascinating is that they present the theoretical possibility of traversable wormholes or closed time-like curves, pathways through spacetime that could in principle connect different regions of the universe or even different times, suggesting that within the mathematics of rotation lies the seed of possibilities that seem to violate our intuitive sense of causality and isolation. As we approach the final frontier of theoretical physics, we encounter one of the most elegant mathematical descriptions of reality that exists in the equations of general relativity. The Reissner-Nordström solutions, which describe black holes that possess electric charge rather than existing in the neutral state that most of us imagine when we think of these cosmic objects. These solutions, discovered in the early 20th century, represent a fundamental extension of the Schwarzschild metric that Karl Schwarzschild first derived, and they reveal that when a black hole carries electrical charge, the very geometry of spacetime around it transforms in profound and counterintuitive ways that challenge our basic intuitions about how reality should behave. The mathematics shows us that charged black holes possess not one event horizon, but potentially two distinct event horizons, an outer horizon and an inner Cauchy horizon, creating a nested structure of trapped regions where the normal rules of causality and physics begin to blur and become strange in ways that keep physicists awake at night contemplating their implications. What makes these solutions psychologically fascinating is that they demonstrate how a single additional property, electric charge, can fundamentally alter the structure of spacetime itself, introducing mathematical features like naked singularities under certain conditions where the protective event horizon simply vanishes, leaving the raw singularity exposed to the universe in violation of Penrose's cosmic censorship conjecture, which most physicists desperately hope is true. We have normalized these equations despite their almost supernatural implications, because they emerge naturally from the very same general relativity that describes gravitational waves we have detected and the bending of light around ordinary massive objects we observe constantly, suggesting that if our theory is correct, these exotic struck